There is a single number that explains almost everything about the seasons, 23.5. That is the number of degrees by which Earth's rotational axis leans away from perfectly upright, tilted relative to the plane of its orbit around the Sun. It is a modest-sounding figure, less than a quarter of a right angle, and yet it is responsible for the full drama of seasonal change that shapes every ecosystem on Earth, every agricultural tradition, every cultural calendar, every migratory pattern, and every moment of biological life that is tuned to the rhythm of the year. Without that 23.5-degree tilt, Earth would be a world without seasons, wrapped in a permanent and uniform climate at every latitude, unvarying from month to month and year to year. With it, the planet pulses with one of the most consequential rhythms in the natural world. To understand why this angle matters so profoundly, it helps to picture Earth as a spinning ball moving around the Sun in a roughly circular path that astronomers call the ecliptic plane. If Earth's rotational axis were perfectly perpendicular to this plane, standing straight up like a perfectly balanced top, every point on the planet's surface would receive the same amount of solar radiation every day of the year. The length of day and night would be equal everywhere, always 12 hours each. The Sun would rise and set at the same angle, and the same points on the horizon, every single day. There would be no summer, no winter, no spring, no autumn. The equator would be warm and the poles cold, as always. But these temperature differences would be absolutely constant, unchanging with the months. But Earth does not stand straight. Its axis tilts, and that tilt maintains a fixed orientation in space. As Earth orbits the Sun over the course of a year, this is the crucial detail that transforms a simple geometric lean into the entire machinery of the seasons. The axis does not tip toward the Sun and then tip back again like a metronome. Instead, it points in a constant direction in space, toward the star Polaris in the northern celestial hemisphere, regardless of where Earth is in its orbit. This means that for half of each year, when Earth is on one side of the Sun, the northern hemisphere's pole is angled toward the Sun. For the other half, when Earth has moved to the opposite side of its orbit, the same pole is angled away. The geometry changes, not because the tilt changes, but because Earth has moved to the other side of the Sun, while keeping its tilt aimed in the same direction. When the northern hemisphere is tilted toward the Sun, three things happen simultaneously that together produce summer. First, the Sun climbs higher in the sky at noon, sometimes approaching directly overhead at tropical latitudes. A higher sun means that its light strikes the ground at a steeper, more concentrated angle, delivering more energy per square meter of surface. Second, the day becomes longer. The circle of daylight, the line separating the sunlit half of Earth from the dark half, is shifted so that a greater fraction of the northern hemisphere's rotation occurs in the light. This means more hours of solar heating per day. Third, the atmosphere itself accumulates warmth over successive days of long, intense sunlight, gradually warming the land, the oceans, and the air itself in the weeks following the solstice. All three of these effects compound each other to produce the heat of summer. When the northern hemisphere is tilted away from the Sun, all three effects reverse. The Sun sits low in the sky at noon, its light arriving at a shallow angle that spreads the same energy across a much larger area of ground, eating each square meter far less efficiently. The day is short. In December at the latitude of New York or London or Beijing, the Sun may be above the horizon for only 8 or 9 hours, compared to 15 or 16 in June, and the atmosphere, depleted of heat by successive short weekdays, grows progressively colder as winter deepens. The same 23.5-degree tilt that created the abundance of summer is now creating the austerity of winter. The magnitude of this effect scales dramatically with latitude. Near the equator, the axial tilt produces only modest seasonal variation. Even in the most tilted position, the equatorial sun never gets very far from directly overhead, and the day length never varies more than a small amount from 12 hours. The result is that equatorial regions have no true seasons in the temperate sense of the word. only the modest variation between wet and dry periods, driven by the shifting of rainfall belts rather than by temperature change. As you move poleward, however, the tilt's effects grow rapidly more pronounced. At 45 degrees latitude, the noon sun's altitude varies by 47 degrees between summer and winter solstice. At 60 degrees, the variation in day length from summer to winter exceeds 12 hours. At the polar circles, the extremes become total, with the midnight sun of summer giving way to the polar night of winter in an annual cycle of unbroken light, followed by unbroken darkness. The stability of this 23.5-degree tilt is itself a remarkable and fortunate fact. The tilt does change slowly over time, cycling between about 22.1 and 24.5 degrees over a period of roughly 41,000 years, in a cycle driven by the gravitational tugs of Jupiter, Saturn, and the other planets. At its steepest, the tilt would produce more extreme seasons than we currently experience. At its shallowest, the seasons would be more muted. These long-term changes in tilt we believe to be one of the factors driving the ice ages that have repeatedly expanded polar ice sheets across large portions of the northern hemisphere over the past several million years. But on human timescales, the tilt is effectively constant, a fixed architectural feature of our planet's geometry that we inherit unchanged from the geological past and pass unchanged to our descendants. The moon plays a critical role in stabilizing this tilt against more chaotic variation. Computer simulations of Earth's motion without the moon show that the gravitational perturbations from the other planets would cause Earth's axial tilt to vary wildly over millions of years, potentially ranging from near zero to more than 80 degrees. Such variation would produce climate swings of catastrophic magnitude, far beyond what life as we know it could stably adapt to. The moon's gravitational influence damps these perturbations, keeping the tilt within its narrow 2.4-degree range of variation and ensuring the relative climatic stability that has characterized Earth over the billions of years during which complex life evolved. We owe the predictable seasons, and perhaps the existence of complex life itself, partly to the presence of an unusually large moon that happened to form from a cataclysmic early collision. The 23.5-degree tilt is ultimately the reason that almost everything in the biological world has a seasonal character. The migrations of birds and whales, the flowering of plants, the breeding cycles of mammals, the agricultural calendars of every farming civilization, the festival traditions of every human culture that has ever existed in the temperate or polar zones. All of these are adaptations to or expressions of the annual rhythm that a tilted axis produces as it circles a star. The seasons feel intimate and immediate, tied to the smell of rain on summer pavement or the sea, crunch of frost underfoot on a December morning. But they reach back, through those sensory surfaces, to a single fixed geometric fact: a planet leaning through space at 23.5 degrees, orbiting a star, creating the year. Twice each year, something subtle and ancient happens in the sky, above every point on Earth. The sun, which has been climbing progressively higher in the noonday sky for 6 months, or sinking lower for 6 months, reaches its extreme and pauses. For a few days clustered around the solstice date, the noon sun appears to rise to the same altitude each day, neither climbing further nor beginning its return. Then, almost imperceptibly at first, and then with gathering speed, it reverses direction. To ancient observers who watched the sky with the meticulous attention that their agricultural and navigational lives demanded, this apparent pause of the sun was one of the most significant events of the year, a turning point in the cosmic order that marked the beginning of a new phase of the annual cycle and called for ritual, ceremony, and careful astronomical observation. The word they eventually gave to these moments carries their observation directly: solstice, from the Latin sol for sun and sister, meaning to stand still. The solstice is not merely a cultural or observational event, but a precise astronomical moment defined by the geometry of Earth's orbit. The summer solstice in the northern hemisphere, which falls on approximately June 20th, or 21 each year, is the instant when the North Pole reaches its maximum tilt toward the sun, at an angle of exactly 23.5 degrees. At this moment, the sun is directly overhead at noon, at the Tropic of Cancer, the line of latitude at 23.5 degrees north. This is the northernmost point at which the sun can ever be directly overhead anywhere on Earth, a fact that defines what a tropic is. Above the Arctic Circle, at 66.5 degrees north latitude, the sun on this day completes a full 360-degree loop around the horizon, never dipping below it, producing the continuous daylight of the midnight sun. Simultaneously, below the Antarctic Circle in the southern hemisphere, the sun never rises at all, and the southern polar night has begun. The winter solstice, falling around December 21st or 22 in the northern hemisphere, is the exact geometrical mirror image of this arrangement. Now the South Pole is maximally tilted toward the sun, and the sun stands directly overhead at noon at the Tropic of Capricorn, 23.5 degrees south. The Arctic Circle experiences its polar night, with the sun never rising. The Antarctic Circle basks in its midnight sun. For every observer in the northern hemisphere, December 21st is the shortest day of the year, the day with the fewest hours between sunrise and sunset, and the sun traces its lowest and most abbreviated arc across the sky. The apparent standstill of the sun around the solstice dates is a real observational phenomenon that results from the mathematics of how the sun's declination, its angular position, north or south of the celestial equator, changes across the year. The sun's declination follows a sinusoidal curve, moving from 0 at the March equinox to its maximum of 23.5 degrees north at the June solstice, back to 0 at the September equinox, and to its minimum of 23.5 degrees south at the December solstice. Near the solstices, the sun is at the top or bottom of this curve, where a sinusoid's rate of change is at its slowest. The day-to-day change in the sun's noon altitude is tiny, only a fraction of a degree, whereas near the equinoxes the sun's altitude changes by several tenths of a degree per day. This is why the sun truly does appear to pause at the solstice, and why it seems to rush through its changes near the equinox. The cultural significance of the solstices across human civilization is impossible to overstate. Virtually every ancient society that has left archaeological or historical records observed and marked the solstices with buildings, rituals, festivals, and astronomical instruments of one kind or another. Stonehenge in England, the most famous of many megalithic monuments, aligned with solar events, is oriented so that the sunrise on the summer solstice occurs precisely over the heel stone, a large sandstone monolith positioned outside the main circle. Whether Stonehenge was primarily a religious site, an astronomical calendar, a place of healing, or some combination of all three remains debated by scholars, but its solar alignment is intentional and precise, reflecting a level of astronomical knowledge and engineering capability that commands respect across a gap of more than 4,000 years. In the ancient world, the winter solstice held particular emotional and spiritual significance. It was the longest night, the moment of maximum darkness, but also the pivot point at which the light began to return. For agricultural peoples dependent on the sun's warmth for their survival, the return of the sun after the solstice was not merely a pleasant seasonal milestone, but a matter of profound relief and gratitude. Festivals of light and fire clustered around the winter solstice in cultures from Scandinavia to Persia to China. The Norse Yule, the Roman Saturnalia, the Persian Yule night, the Jewish Hanukkah, and many others all share the theme of fire and light, kindled against the longest darkness of the year. The Christian celebration of Christmas was positioned near the winter solstice, whether by deliberate adoption of existing solar festivals or by other historical processes, and it retains to this day the themes of light born in darkness and hope renewed in the depths of winter. The precision with which ancient astronomers tracked the solstice is remarkable given the tools available to them. Determining the exact date of the solstice requires measuring the sun's noon altitude with enough precision to detect the tiny day-to-day changes near the turning point, changes that can be as small as a few arc minutes. Ancient astronomers accomplished this with gnomon shadows, carefully constructed horizon markers, and the patient accumulation of observations over many years. The Egyptian astronomer Eratosthenes used the behavior of a gnomon shadow at the summer solstice in Alexandria, and the observation that there was no shadow at noon on the same day in the city of Sion, 800 kilometers to the south, to calculate the circumference of the Earth with an accuracy that remained unsurpassed for centuries. The solstice was his laboratory instrument. In the modern world, the solstices retain their significance both as astronomical events and as cultural moments. The summer solstice is celebrated at Stonehenge each year by thousands of people who gather to watch the sunrise over the heel stone, continuing an observational tradition that stretches back millennia. Midsummer festivals are held across Scandinavia and Northern Europe, lighting bonfires and dancing through the brief summer night in a direct echo of pre-Christian seasonal celebration. The winter solstice has seen a revival of interest as a marker of the astronomical turning of the year, observed by people who feel the power of this cosmically significant moment independently of any particular religious tradition. The solstices remind us that our calendar is not merely a human invention, but a shadow of cosmic geometry, a way of marking and naming moments in Earth's orbital journey that would occur and recur with or without human observation. Every June 21st, whether anyone is watching or not, the North Pole reaches its maximum tilt toward the sun. The sun pauses at its highest point, and the slow reversal begins. Every December 21st, the darkness reaches its deepest, and the light, imperceptibly at first, begins to return. These are real moments in the physics of the solar system, as fixed and as certain as the laws of gravity themselves. And the fact that human beings across thousands of years and dozens of cultures have felt them to be worthy of celebration says something important about the depth of our connection to the astronomical machinery of which we are, in the end, a very small but deeply attentive part. On 2 mornings each year, at locations spread across the entire face of the Earth, the sun rises at a point on the horizon that is precisely due east, not approximately east, not close to east, but true east, the exact direction that points directly toward the celestial equator along the horizon. On those same evenings, it sets at exactly true west. Everywhere in the world, from the equator to the poles, from the busiest city to the most remote wilderness, the sun rises and sets at these 2 precise cardinal points. The day lasts approximately 12 hours. The night lasts approximately 12 hours. The world is, for one brief moment in its annual cycle, in a state of something approaching perfect balance between light and dark. This is the equinox, a word that means equal night in Latin, and it occurs twice each year, once in March and once in September. The equinox is the precise astronomical moment when Earth's axis is oriented neither toward the sun nor away from it, but exactly sideways relative to the Sun-Earth line, because Earth's axis maintains its fixed tilt in space. As the planet orbits the sun, there are 2 points in each orbit when the axis is perpendicular to the line connecting Earth's center to the sun's center. At these moments the terminator, the lin, that divides Earth's sunlit hemisphere from its dark hemisphere, passes directly through both poles. This is what causes day and night to be equal everywhere simultaneously. When the terminator passes through the poles, every point on Earth's surface spends exactly half of its daily rotation in the light and half in the dark. The March equinox, which falls around March 19th, 20 or 21 depending on the year, is called the vernal equinox in the northern hemisphere, from the Latin word var meaning spring. It marks the moment when the sun crosses the celestial equator, moving northward, which astronomers define as 0 degrees of declination. After this moment, the noon sun in the northern hemisphere will continue climbing higher in the sky each day, and the days will continue lengthening until the June solstice. In the southern hemisphere, this same moment is the autumnal equinox, the beginning of autumn and the start of the progression toward shorter days and lower sun angles. The September equinox, falling around September 22nd or 23, reverses this arrangement bringing astronomical autumn to the northern hemisphere and spring to the southern. A subtlety that surprises many people is that the equinox does not actually produce exactly equal day and night at most latitudes on Earth. The technical 12-hour day and 12-hour night occurs a few days before the March equinox, and a few days after the September equinox, a discrepancy caused by two factors. The first is atmospheric refraction. The atmosphere bends sunlight around the curve of the Earth, allowing the sun to be seen above the horizon when it is actually geometrically just below it. This bending adds several minutes of visible sunlight to each end of the day. The second factor is that the definition of sunrise and sunset is the moment when the upper limb of the sun, not its center, crosses the horizon. Since the fact E-sun has an angular diameter of about half a degree, this adds roughly a minute at each end. The combined effect of these two factors means that the day when day and night are truly equal in length is shifted slightly from the astronomical equinox date. The equinoxes mark the transition points between Earth's seasonal extremes, the moments when the annual pendulum of solar heating passes through its center point on its way from one extreme to the other. This makes them the natural starting points for the astronomical definition of seasons. Spring begins at the March equinox, summer at the June solstice, autumn at the September equinox, and winter at the December solstice in the northern hemisphere. This definition, while astronomically precise, differs from the meteorological definition used by climate scientists who define the seasons by calendar months. Meteorological spring is March, April, and May. Summer is June, July, and August, and so on. The offset between these two definitions reflects the seasonal lag discussed elsewhere. The delay between astronomical turning points and the corresponding temperature extremes caused by the thermal inertia of land and ocean. Across human civilizations, the equinoxes have been observed and celebrated with a consistency that rivals even the solstices. The March equinox has served as the beginning of the new year in numerous historical calendar systems, including the ancient Persian, Babylonian, and Hebrew calendars, and it retains this role in the Iranian New Year celebration of Nowruz, which has been observed for at least 3,000 years and is now inscribed on UNESCO's list of intangible cultural heritage. Nowruz literally means new day in Persian, and it celebrates the moment when day and night stand equal, winter ends, and the season of growth begins. The festival is observed by hundreds of millions of people across Iran, Central Asia, the Caucasus, and the Kurdish regions of the Middle East, representing one of the oldest continuously observed astronomical celebrations in human history. Easter, in the Christian calendar, is defined in relation to the March equinox. It falls on the first Sunday after the first full moon following the spring equinox. This definition, established by the First Council of Nicaea in 325 CE, connects the most important Christian festival to a combination of solar and lunar astronomical events, the equinox and the full moon, in a way that preserves an astronomical observational heritage reaching back to the ancient Jewish Passover calendar on which it was originally based. The result is a festival that wanders across a wide range of dates from year to year, sometimes falling in late March, and sometimes not until late April, because the moon's cycle does not fit neatly into the solar year. The equinox has also served as a zero point, or reference moment in astronomical observation. Across many cultures, the position of the sun at the March equinox defines the first point of Aries, the reference point from which the positions of all other celestial objects are traditionally measured in the coordinate system called the ecliptic. Because of the precession of Earth's axis, a slow wobble that causes the axis to trace a circle in space over 26,000 years, the March equinox point has shifted from the constellation Aries, where it was when ancient astronomers named it, into the constellation Pisces, and is slowly moving toward Aquarius, a fact that underlies the astrological concept of the age of Aquarius. The astronomical history encoded in these names is a record of how carefully and continuously human beings have observed the equinox point across more than 2,000 years of sky watching. for the observer standing anywhere on Earth on the morning of an equinox. The experience is simple and beautiful. The sun rises from the due east horizon, traces a gentle arc across the sky that passes through the due south point at noon and sets precisely at due west as evening comes. The day is exactly as long as the night. The world is, by one measure, in perfect balance, poised between the increasing warmth of spring and the declining light of autumn, between the growing light and the growing dark. This balance lasts only a moment before the progression resumes, but for that moment the equinox offers a still point in the annual turning of Earth, a pause in the seasonal pendulum at the exact center of its swing. There is something that feels almost like a philosophical puzzle in the following fact. On the same day that a child in Sweden is building a snowman, a child in New Zealand is cooling off in a swimming pool, while a farmer in Canada is watching the last of the harvest frost crystallize on the stubble of his fields. A farmer in Argentina is watching his wheat put up its first green shoots, while the streets of Moscow are buried in snow, and the days shrink to a thin sliver of gray winter light. The streets of Cape Town are baking under long, brilliant summer days. These pairs of simultaneous, opposite realities are not coincidences or anomalies. They are the precise, mathematically inevitable consequence of a tilted planet, a result so geometrically direct that once you understand the mechanism, it seems almost obvious. Yet it continues to feel surprising, even to people who know it intellectually, that the seasons of the two hemispheres are mirror images of each other, playing out in permanent and perfect opposition. The mechanism, as with so much about the seasons, begins with Earth's axial tilt. The axis leans at 23.5 degrees from perpendicular to the orbital plane, pointing in a fixed direction in space as Earth orbits the 4-5 Sun for approximately half the year, from the March equinox to the September equinox. The North Pole is tilted toward the Sun. During this period, the Northern Hemisphere receives sunlight at a higher angle. The days are longer, and the cumulative solar energy per unit area per day is greater than the Southern Hemisphere receives. The Northern Hemisphere experiences spring and summer. At the same time, the South Pole is tilted away from the Sun by exactly the same angle. The Southern Hemisphere receives sunlight at a lower angle. Its days are shorter, and it receives less solar energy per unit area per day. The Southern Hemisphere experiences autumn and winter. From the September equinox to the March equinox to the March equinox, Earth is on the other side of its orbit, and the arrangement is exactly reversed. Now the South Pole tilts toward the Sun, and the Southern Hemisphere moves through its spring and summer. Simultaneously, the North Pole tilts away, and the Northern Hemisphere experiences its autumn and winter. The two hemispheres are permanently out of phase with each other by exactly 6 months, as reliably and precisely as the two ends of a seesaw, one of which must be up whenever the other is down. This hemispheric opposition has consequences that extend far beyond the simple observation that Australia has a hot Christmas while Canada has a cold one. The timing of seasonal phenomena in the two hemispheres, from animal migrations to agricultural cycles to ocean circulation patterns, is offset by this same 6-month displacement, and the interactions between the two offset systems create some of the most important and complex dynamics in Earth's climate. The ocean is perhaps the most important arena in which hemispheric opposition plays out on a global scale. The Southern Hemisphere contains a much larger proportion of ocean surface than the Northern Hemisphere, which has significantly more land. Since ocean water has a much higher heat capacity than land, it absorbs and releases heat more slowly. This means that the Southern Hemisphere's seasons are generally less extreme than the Northern Hemisphere's at comparable latitudes. Southern Hemisphere summers are somewhat cooler, and Southern Hemisphere winters are somewhat milder than the corresponding Northern Hemisphere seasons, because the vast Southern Ocean moderates the temperature swings that would otherwise occur. The Antarctic continent is far colder than the Arctic Ocean, because land loses heat more efficiently than water, but the surrounding Southern Ocean keeps the subantarctic islands and the southern tips of the continents from experiencing the extreme continental cold of comparable northern latitudes. The offset of seasons between hemispheres has significant implications for global weather and climate patterns. The intertropical convergence zone, the band of intense rainfall and atmospheric convection that encircles the Earth near the equator, migrates northward during northern hemisphere summer and southward during southern hemisphere summer. This migration is the primary driver of the monsoon systems that deliver the rainfall on which hundreds of millions of people in South Asia, West Africa, and the Americas depend for their agriculture and their water supplies. The seasonal heating of the northern hemisphere in summer draws the ITCZ northward, pulling moisture-laden winds across the equator and depositing enormous quantities of rain over South Asia, Sub-Saharan Africa, and Central America. The offset of agricultural seasons between hemispheres has become increasingly important in the context of the global food trade. When the northern hemisphere's wheat crop is harvested in July and August, the southern hemisphere's crop is still in the ground, months from harvest. When Argentina and Australia harvest their wheat in November and December, the northern hemisphere crop has long been stored in silos. This offset means that the world always has a harvest in progress somewhere, a fact that helps smooth the global supply of staple crops and provides a buffer against regional crop failures. If both hemispheres had their harvests at the same time, the global food system would be far more vulnerable to simultaneous bad weather across multiple major growing regions. For migratory species, the hemispheric opposition of seasons creates extraordinary journeys that connect the two opposite extremes of the annual cycle. The Arctic tern is the most famous example, migrating from its Arctic breeding grounds to the Antarctic and back again each year, a round trip of up to 70,000 kilometers. The tern is perpetually following summer, exploiting the long productive days of the polar summer at both ends of its journey. It experiences more daylight hours than any other creature on Earth, spending its entire life moving between two simultaneous summers on opposite sides of the planet. This extraordinary migration is only possible because the seasons of the two hemispheres are precisely offset, ensuring that when Arctic summer ends and autumn closes in, and Antarctic summer is just beginning, the experience of crossing the equator and entering the opposite seasonal hemisphere has been a source of wonder to travelers throughout history. For Europeans, sailing south to trade in the Indian Ocean or establish colonies in South America and Africa, the experience of Christmas in summer heat or of the August sun blazing in a sky that should, by all bodily memory, belong to deep winter was profoundly disorienting. It remains so today for anyone who has grown up in one hemisphere and crosses into the other. The body's expectations, tuned to a lifetime of seasonal associacy, are confounded by a reality that the intellect understands perfectly, but the senses find strange. Summer in December still feels wrong to a northern hemisphere native, just as winter in July does to someone raised in the South. This visceral sense of seasonal wrongness of the world turned upside down is one of the most immediate and personal ways in which the hemispheric opposition of seasons makes itself felt in human experience. There is a puzzle embedded in the way we experience the seasons that most people notice, but few take the time to think through carefully. The longest day of the year, the summer solstice, falls around June 21st in the northern hemisphere. By astronomical definition, this is the peak of summer, the moment of maximum solar energy input, the day when the sun reaches its highest point in the sky and stays above the horizon the longest. And yet, almost universally, the hottest days of the year in the northern hemisphere come not in late June but in July and August, weeks after the sun has already begun its retreat toward the horizon. Similarly, the winter solstice falls around December 21st, the shortest day of the year, the astronomical dead of winter, yet the coldest days most reliably occur in January and February, not in late December. Why does the temperature peak come so long after the solar peak? Why does winter's coldest grip tighten after the days have already begun to lengthen? The answer lies in one of the most important concepts in climate science, thermal inertia. Thermal inertia is the tendency of a large body of material to resist changes in temperature, to continue warming even after the rate of heat input has begun to decrease, and to continue cooling even after the rate of heat loss has begun to decline. It is the same property that makes a cast iron pan hold its heat long after the burner beneath it has been turned off, or that keeps a beach warm for hours after the sun has set. On a planetary scale, thermal inertia is primarily provided by the oceans, and to a lesser extent by the land and the lower atmosphere. These enormous reservoirs of heat take a long time to warm up and an equally long time to cool down, and their slow response to changing solar input is the reason that temperatures lag behind the astronomical seasons by 4 to 6 weeks. The oceans are the dominant player in this system. Water has a very high specific heat capacity, meaning it requires a large amount of energy to raise its temperature by a given amount compared to soil, rock, or air. The world's oceans, which cover about 71% of Earth's surface and have an average depth of about 3,800 meters, represent an almost inconceivably large thermal reservoir. When the days begin to lengthen after the winter solstice in December, the sun is climbing higher in the sky and delivering more energy per hour and per day. But for months afterward, the ocean's top layers are still releasing the stored heat of the previous year, and the net effect is continued cooling of the air above them. The ocean's surface temperature in the northern Atlantic, for instance, is typically coldest not in December or January, but in February or even early March, months after the solar input has begun its post-solstice increase. The land responds more quickly than the ocean, but still shows substantial lag. Soil and rock have lower heat capacities than water and conduct heat less efficiently, so they gain and lose heat faster, but still show a meaningful delay relative to the astronomical seasons. In strongly continental climates, far from the moderating influence of the ocean, the temperature lag is somewhat smaller than in maritime climates, and the seasonal extremes are more closely aligned with the astronomical solstices and equinoxes. But even in the most continental of climates, the coldest and hottest days come weeks after the astronomical turning points. The atmospheric response to changing surface temperatures adds another layer of delay. The lower atmosphere is heated primarily by contact with the warm surface below, rather than directly by the sun above, so it tracks the surface temperature with its own additional lag. As the ocean and land warm after the solstice, the air above them gradually warms as well, reaching its peak temperature weeks after the surface below has reached its own peak. The compounding of these sequential lags, solar input driving surface temperature, driving atmospheric temperature, is what ultimately produces the seasonal temperature pattern that humans experience, with the hottest and coldest days falling well after the astronomical turning points. The seasonal lag has important practical consequences for agriculture, ecology, and human comfort that are not always recognized. The timing of the last spring frost and the first autumn frost, which define the growing season for crops in temperate regions, follows the temperature cycle rather than the astronomical cycle. In the northern hemisphere, the last frost typically occurs in April or May, weeks after the vernal equinox, and the first autumn frost comes in September or October, weeks after the autumnal equinox. A farmer timing planting and harvesting decisions by the astronomical calendar would systematically plant too early and harvest too late. The experiential seasonal calendar, built up over generations of agricultural observation, tracks the temperature cycle correctly, which is why the traditional dates for spring planting fall in April and May, rather than immediately after the March equinox. Ecologically, the seasonal lag creates an important offset between the availability of sunlight and the availability of warmth that shapes many biological timing decisions. Plants that use day length as their cue to flower or break dormancy will respond to the lengthening days of spring before the temperatures are warm enough to support their growth, a mismatch that natural selection has resolved in various ways. Many plants use a combination of day length and temperature cues, requiring both a minimum photo period and a minimum number of warm days before they commit to flowering. This dual Q system buffers them against the risk of breaking dormancy prematurely during warm spells in early spring, before temperatures have stabilized enough to support sustained growth. The seasonal lag is also of fundamental importance for understanding climate change and its impacts. As the climate warms globally, both the average temperatures and the timing of seasonal events are shifting. Spring is arriving earlier as measured by biological indicators, like blood break insect emergence and bird migration, and autumn is arriving later. The length of the frost-free season is extending, but these shifts are not uniform across different indicators, and the seasonal lag means that some biological systems are tracking temperature more faithfully, while others are tracking day length, which has not changed. The resulting mismatches between interacting species, such as the timing of flower blooming and the emergence of the insects that pollinate them, or the arrival of migratory birds and the peak abundance of the insects on which they feed their young, are among the most concerning ecological consequences of rapid climate change. The seasonal lag is, in the end, the planet's way of smoothing out the sharp edges of the astronomical calendar. The solstices and equinoxes are instantaneous geometric events, precisely defined moments in the mathematics of orbital mechanics. The seasons, as humans and other organisms experience them, are the blurred, delayed, dampened response of a complex thermal system to those precise astronomical signals. The lag is what transforms the sharp click of the astronomical turning point into the gradual rounded arc of the felt season, making the transition from summer to autumn a weeks-long process of gradual cooling rather than an abrupt shift on the day after the solstice. It is the memory of the planet, the thermal record of every previous day, written into the temperature of the ocean and the soil and the air, shaping the present moment through the weight of accumulated past. Cross the equator anywhere in the world, and you enter a climate that most people who grew up in the temperate zones find subtly and persistently disorienting. The temperatures are consistently warm, hovering in a range that most temperate zone inhabitants would associate with the height of summer, without the relief of a cool autumn or the bracing contrast of winter. The days are consistently close to 12 hours long throughout the year, with only modest variation from one month to the next. The sun rises and sets at roughly the same angles day after day, climbing to nearly overhead at noon in every month, never retreating to the low, slanted winter angles that give temperate landscapes their most dramatic light. The rhythms of daily life are governed less by the march of astronomical seasons than by rainfall patterns, by the alternation of wet and dry seasons, driven by the shifting of atmospheric pressure belts, rather than by the changing tilt of the sun. For those who know it, the equatorial world has its own profound beauty and its own deep seasonal rhythms. But they are not the seasons of the middle latitudes, and the absence of that familiar four-beat annual rhythm leaves many travelers feeling that something fundamental is missing from the year. The reason for the near disappearance of temperature-based seasons at the equator is straightforward and geometrically inevitable. The equator is the line around Earth that is always equally distant from both poles, and Earth's 23.5-degree axial tilt affects it very differently than it affects higher latitudes. At the equator, even at the solstices when the tilt is at its maximum effect, the sun at noon is never more than 23.5 degrees away from directly overhead. In June, when the sun is directly overhead at the Tropic of Cancer in the northern hemisphere, the equatorial noon sun is 23.5 degrees south of the zenith. In December, it is 23.5 degrees north of the zenith. These are modest deviations from overhead, and the difference in solar intensity between the most overhead and least overhead positions at the equator is not large enough to produce the dramatic temperature swings of temperate latitudes. Day length at the equator is similarly invariant, because the terminator, the boundary between the sunlit and dark halves of Earth, always passes through the poles. Every point on the equator lies in the middle of the sunlit hemisphere for exactly half of each rotation, and in the dark hemisphere for exactly half. This is true regardless of where Earth is in its orbit, regardless of the tilt of the axis. The equatorial day is always 12 hours plus a few minutes, and the night is always 12 hours minus a few minutes throughout the year. Without the long summer days that deliver extra hours of solar heating at higher latitudes, or the long winter nights that allow extended radiative cooling, the equatorial regions receive a consistent, moderate daily dose of solar energy every day of the year. The result of these two factors, consistent solar angles and consistent day length, is a climate characterized by remarkably stable temperatures throughout the year. Quito, Ecuador, sits almost exactly on the equator at an altitude of about 2,850 meters and experiences average monthly temperatures that vary by only about 1 degree Celsius from the coolest month to the warmest. Singapore, at just over 1 degree north of the equator, has average monthly temperatures that vary by less than 2 degrees Celsius throughout the year. The temperature range between the coolest and warmest hours of a single day in these cities is often larger. The temperature range between the coolest and warmest months of the year. This thermal consistency, so alien to temperate zone sensibilities, is the direct result of the equator's geometrically special relationship. But to say that the equatorial world lacks seasons is to impose a temperate zone definition of what a season is. The equatorial tropics are far from seasonless. They simply have a different seasonal structure, organized around rainfall rather than temperature. The fundamental driver of equatorial seasonal variation is the Intertropical Convergence Zone, or ITCZ, a belt of intense atmospheric convection and rainfall that encircles the Earth near the equator and migrates north and south with the seasons in response to the changing position of the sun's overhead point. When the ITCZ passes over a given location, it delivers heavy regular rainfall that transforms the landscape. Rivers flood, vegetation explodes into growth, animals breed, and the air is filled with the sound and smell of rain. When the ITCZ moves away, rainfall diminishes or ceases, the landscape dries, rivers shrink, and many organisms enter states of dormancy or migrate in search of water. Many equatorial regions therefore experience 2 wet seasons and 2 dry seasons each year, as the ITCZ passes over them twice annually on its way north and then on its way back south. Some locations experience a more asymmetric pattern, with 1 dominant wet season and 1 dry season, depending on the precise movement of the ITCZ and the influence of local geography. The rainforest of the Congo Basin, the Amazon, and much of Southeast Asia are sustained by this reliable equatorial rainfall regime, which delivers 2 to 4 meters of rainfall per year in many places, supporting the richest terrestrial biodiversity on Earth. Farmers in equatorial Africa and Asia have developed sophisticated agricultural systems calibrated to these wet, dry seasonal rhythms. Planting with the onset of the rains and harvesting before the dry season reduces soil moisture below a critical threshold. The cultural and biological adaptations to equatorial seasonality are as deep and as elaborately developed as those of temperate societies to the 4-season cycle, but they are organized around a fundamentally different set of seasonal signals, rather than the changing angle and duration of sunlight. Equatorial cultures read the seasons in the behavior of the rain, the state of rivers, the availability of particular foods, and the flowering and fruiting cycles of plants that respond to moisture rather than temperature. Many equatorial agricultural calendars mark time by the seasonal availability of particular crops, by the behavior of fish in rivers during flood and low water periods, and by the timing of traditional festivals that correspond to the rhythms of planting and harvesting in the local agricultural system. The equatorial world is a reminder that the 4-season model of the year, so deeply embedded in the cultural frameworks of temperate zone civilizations, is a product of latitude rather than a universal feature of planetary experience. For roughly a third of humanity living in the tropical zone, the year is organized by different environmental rhythms and different seasonal relationships between human life and the natural world. The seasons are no less real, no less consequential, and no less deeply woven into cultural identity and biological adaptation in equatorial regions than in temperate ones. They are simply different. organized by the rainfall that the astronomical seasons indirectly produce, rather than by the temperature contrasts that the tilt of the axis creates directly. Imagine standing on an ice field somewhere above the Arctic Circle on a June night at midnight. The sky is bright, not the bright of full noon, but a clear, luminous, golden blue light that fills the entire dome of the sky, casting long, soft shadows across the ice and making the snow surfaces glow with warm color. The sun hangs above the northern horizon, neither rising nor setting, simply circling the sky in a slow, unbroken loop that it has been tracing for weeks and will continue to trace for weeks more. There is no darkness. There will be no darkness tonight. There will be no darkness for weeks. This is the midnight sun, one of the most extraordinary experiences available to any observer of the natural world, and it is the direct, inevitable consequence of Earth's axial tilt taken to its logical extreme at the polar regions. The phenomenon occurs because of the way that Earth's tilt interacts with the geometry of day and night at high latitudes. At the Arctic Circle, 66.5 degrees north, there is exactly 1 day per year when the sun does not set, the summer solstice. On this day, the sun just grazes the northern horizon at midnight and immediately begins climbing again toward noon. Above the Arctic Circle, the period during which the sun does not set grows progressively longer with increasing latitude. At 70 degrees north, the midnight sun lasts about 2 months. At 80 degrees north, it lasts more than 4 months. At the North Pole itself, the sun rises once around the spring equinox and sets once around the autumnal equinox, meaning that the pole experiences approximately 6 months of continuous daylight, followed by 6 months of continuous darkness, with brief transitional twilight periods between. The physics behind this is elegant. The terminator, the line dividing the sunlit and dark halves of Earth, always passes through the poles at the equinoxes when the axis is sideways relative to the sun. But at the summer solstice, when the North Pole is tilted 23.5 degrees toward the sun, the terminator is tilted as well. At any latitude above 66.5 degrees north, the entire circle of latitude lies within the sunlit hemisphere for the full 24 hours of Earth's rotation. A point at 70 degrees north, rotating around Earth's axis over the course of the day, never crosses into the shadow side. The sun appears to circle the sky rather than rising and setting, varying in altitude as the observer's rotation carries them toward the anti-solar direction and back, but never dipping below the horizon. The ecological consequences of continuous summer sunlight above the Arctic Circle are profound and create one of the most dramatically productive ecosystems on Earth. Arctic plants, which spend most of the year dormant under snow, emerge in spring and race to complete their entire annual cycle of growth, flowering, and seed production in the brief window of summer availability. Many Arctic plant species grow with extraordinary speed, driven by the continuous availability of sunlight around the clock. The productivity of Arctic tundra during the brief summer can rival that of much warmer temperate ecosystems, precisely because the photosynthesis that normally occurs over 12 daylight hours is instead occurring over 24, doubling the daily energy capture for the plants that can exploit it. This explosion of plant productivity supports enormous summer populations of insects, birds, fish, and mammals that migrate to the Arctic to exploit this seasonal abundance. Migratory birds are perhaps the most dramatic exploiters of Arctic summer productivity. Hundreds of species breed in the high Arctic, taking advantage of the endless summer days to raise their chicks in an environment that offers both abundant food and continuous daylight for foraging. Shorebirds that breed on Arctic tundra can feed their chicks around the clock, a strategy that allows for much faster chick development than is possible in temperate regions where night curtails foraging activity. Many Arctic breeding shorebird chicks achieve full growth and independence in fewer than 3 weeks, a remarkable developmental speed enabled entirely by the continuous daylight of the Arctic summer. The reverse of the midnight sun is the polar night, the period during which the sun does not rise above the horizon. At the Arctic Circle, this too is limited to a single day at the winter solstice. Above the circle, the polar night grows longer with increasing latitude, reaching 6 months at the North Pole. The polar night is not, as many people imagine, a period of absolute darkness. Above the Arctic Circle in winter, even when the sun is below the horizon, there are extended periods of civil twilight, nautical twilight, and astronomical twilight, as the sun traces its circle just below the horizon, illuminating the sky to varying degrees. Near the polar circle, the midday twilight of deep winter is bright enough to read by. In truly high Arctic latitudes, the midday sky takes on the deep blue of late dusk, and the landscape is illuminated by a ghostly, shadowless blue light quite unlike anything seen in temperate or equatorial regions. The physiological and psychological effects of the polar light extremes on the human beings who live through them are well documented and have shaped the cultures of Arctic peoples in profound ways. The continuous light of the Arctic summer disrupts circadian rhythms and sleep patterns in visitors unaccustomed to it. The brain's melatonin system, which uses darkness as its primary signal to initiate sleep, finds it impossible to read a night that never arrives. Residents of Arctic communities develop cultural adaptations, including blackout curtains, strict bedtime routines, and a practiced ability to sleep in daylight that visitors lack. Many report a kind of euphoric hyperactivity during the height of the midnight sun, a feeling of boundless energy and reduced need for sleep that reflects the melatonin-suppressing effect of continuous light. The polar winter brings the opposite challenge: the reduction and eventual disappearance of sunlight during the polar night removes not only the circadian light cue that regulates sleep, but also the light exposure that sustains vitamin D synthesis in the skin, and that moderates mood through the serotonin and melatonin systems. Seasonal affective disorder is significantly more common in high-latitude populations than in those living closer to the equator, and the polar communities that experience the most extreme winter darkness have developed the most elaborate cultural responses to the challenge of the dark season. Light therapy, communal gathering, midwinter festivals, and a cultural orientation toward warmth, coziness, and indoor social life serve as adaptive strategies against the psychological weight of the polar winter. In all of these ways, the extreme seasonal light environment of the polar world shapes not just the biology, but the culture, psychology, and social life of the people who inhabit it. The fact that many people carry around a confident but wrong explanation for why the seasons occur is itself an interesting phenomenon, and it speaks to the power of intuition over geometry in the way we make sense of the people world. Ask most people why summer is hot and winter is cold, and a significant proportion will tell you, with genuine conviction, that it is because Earth is closer to the sun in summer. The explanation feels right. Surely, the closer you are to a heat source, the warmer it is. Surely the distance from the sun must be a major factor in how much heat Earth receives. And yet this explanation is not just slightly wrong, it is spectacularly wrong in the opposite direction. Earth is in fact closest to the sun in the northern hemisphere's winter, not summer. At the moment, in its orbit called perihelion, which occurs in the first week of January each year, Earth sits about 147 million kilometers from the sun. At aphelion, its farthest point, reached in early July, Earth is about 152 million kilometers away. The supposedly cold winter months are actually the months when Earth is physically nearest to the sun, by a margin of 5 million kilometers. This fact, which surprises nearly everyone who encounters it for the first time, is a spectacular demonstration of why geometry, not distance, governs the seasons. The 3% variation in Earth-Sun distance across the year does produce a real but modest difference in solar energy received. Earth actually intercepts about 7% more solar radiation per unit area at perihelion than at aphelion, because energy intensity falls off with the square of distance. 7% is not negligible, and the perihelion effect does have measurable consequences for global climate patterns, which we will discuss shortly, but it is dwarfed by the effect of axial tilt, which changes the amount of solar energy received by the northern hemisphere by a factor of 2 or more between summer and winter. 7% cannot compete with 100%. Distance is a minor variable. Angle is the major one. The shape of Earth's orbit is the underlying fact behind the January perihelion. Earth's orbit around the Sun is an ellipse as required by the laws of gravity and orbital mechanics first worked out by Johannes Kepler in the early 17th century. Kepler's first law states that the orbit of every planet is an ellipse with the Sun at one of the two foci of the ellipse. For Earth, this ellipse is only slightly eccentric. It is nearly circular, with an eccentricity of only 0.0167. To visualize how nearly circular this is, if you drew Earth's orbit to scale on a piece of paper, it would look indistinguishable from a perfect circle to the naked eye. The difference in Earth-Sun distance between perihelion and aphelion is small because the orbit is nearly circular, and the seasons we experience are dominated by the effects of axial tilt rather than by this small orbital variation. Kepler's second law governs how Earth's orbital speed changes with distance. Earth moves fastest when it is closest to the Sun, at perihelion in January, and slowest when it is farthest away, at aphelion in July. The difference in orbital speed between perihelion and aphelion is about 3%, meaning that Earth takes slightly longer to travel through the aphelion half of its orbit than through the perihelion half. As a result, northern hemisphere summer, which coincides with the aphelion phase when Earth moves more slowly, is actually slightly longer than northern hemisphere winter. The northern hemisphere summer is about 7 days longer than its winter, because Earth spends those 7 extra days moving more slowly through the aphelion part of the orbit. This is a small but real asymmetry in the length of the astronomical seasons. The coincidence of northern hemisphere winter with perihelion and summer with aphelion is not permanent. The orientation of Earth's orbit relative to its axis slowly rotates over a cycle of about 21,000 years due to gravitational interactions with other planets, a cycle called the precession of the apsides. Currently, perihelion occurs in early January and aphelion in early July, meaning that the northern hemisphere receives slightly more solar energy in winter and slightly less in summer than it would if perihelion occurred during northern hemisphere summer. This slight moderation of northern hemisphere seasons, with winters a touch warmer and summers a touch cooler than they would otherwise be, is believed to be one of the factors that has kept large-scale glaciation relatively suppressed during the current interglacial period. About 11,000 years ago, the apsidal precession cycle was in the opposite phase. Perihelion occurred in northern hemisphere summer and aphelion in winter, giving northern hemisphere summer slightly more solar energy and winters slightly less. This configuration is believed to have contributed to the remarkably warm and humid Holocene climatic optimum of around 6,000 to 9,000 years ago. The southern hemisphere experiences the opposite of the northern hemisphere's perihelion winter coincidence. Southern hemisphere summer occurs when Earth is at perihelion in January, meaning that southern hemisphere summers receive slightly more solar energy than northern hemisphere summers at comparable latitudes. And southern hemisphere winters coincide with aphelion, meaning they receive slightly less solar energy than comparable northern hemisphere winters. The net effect is that southern hemisphere seasons are slightly more extreme in terms of solar energy input than northern hemisphere seasons, though this effect is substantially moderated by the greater ocean coverage of the southern hemisphere, which buffers temperature swings through its enormous heat capacity. Understanding the irrelevance of Earth-Sun distance to the seasons is also a valuable exercise in thinking about scale and proportion. The 5 million kilometer difference between perihelion and aphelion sounds like an enormous distance by any human scale, and it is. It is more than 13 times the distance from Earth to the Moon, and yet, measured against the 150 million kilometer average Earth-Sun distance, it is a variation of only 3%. Meanwhile, The effect of a 23.5-degree tilt on the angle of incoming sunlight changes the energy per unit area by a factor that varies from near zero in winter polar regions to near maximum in summer tropical ones, a variation that dwarfs the distance effect by every measure. The lesson is one that recurs throughout physics and astronomy. Our intuitions about scale and proportion, built up through experience of the human scale world, in the Benno world, are frequently unreliable guides to understanding systems that operate on scales far beyond our direct experience. Stand outside on a clear December noon at 50 degrees north latitude, the latitude of London or Vancouver, and look at the shadow you cast. It is long, remarkably long. Your shadow stretches out ahead of you at an angle that seems almost horizontal compared to the short, compact shadow of a summer noon. When the sun blazes high overhead and compresses your shadow to a puddle at your feet, the length of your winter shadow is telling you something precise and important about why it is cold. It is a visual representation, drawn on the ground beneath your feet, of the angle at which the sun's rays are striking the surface, and that angle is the fundamental reason that winter sunlight, despite arriving from the same sun that provides summer's heat, cannot warm the ground nearly as well. The concept involved is simple enough to explain with a flashlight. Hold a flashlight perpendicular to the surface of a table and shine it downward. The circle of light it produces is compact and bright, concentrating all of the light from the flashlight beam into a small area. Now tilt the flashlight so it shines at a shallow angle. The circle stretches into an oval, then into an elongated ellipse. The same amount of light that illuminated a small circle is now spread across a much larger area. The intensity of the light per unit area, the brightness at any given point, has decreased, even though the flashlight itself has not changed at all. This is precisely what happens to sunlight as it strikes Earth at different angles across different latitudes and different seasons. The mathematical relationship is governed by the cosine of the angle of incidence, the angle at which the sunlight meets the surface. When sunlight comes in at 90 degrees, perfectly perpendicular to the surface, it delivers maximum energy per unit area. As the angle decreases from 90 degrees towards zero, the energy per unit area decreases proportionally to the cosine of the angle from perpendicular, or equivalently to the sine of the elevation angle above the horizon. At a sun elevation angle of 30 degrees above the horizon, the energy per unit area is half what it would be at 90 degrees, because the sine of 30 degrees is 0.5. At 15 degrees elevation, it drops to about a quarter of the maximum value. On a December noon at 50 degrees north latitude, the sun sits only about 16 degrees above the horizon, delivering barely more than a quarter of the energy per unit area that it would deliver if it were directly overhead. Summer, at the same latitude, brings the noon sun to over 60 degrees above the horizon, delivering nearly 90% of the maximum possible intensity. The second reason that shallow-angle sunlight is weak is the increased thickness of atmosphere it must pass through. When sunlight comes in at a low angle, it travels through a much longer path through the atmosphere before reaching the surface than when it comes in at a steep angle. Overhead sunlight, at 90-degree incidence, passes through the atmosphere along the shortest possible path, called one air mass. Sunlight arriving at 30 degrees elevation passes through two air masses of atmosphere. At 10 degrees elevation, the path length through the atmosphere is nearly 6 air masses. Each additional air mass of atmosphere absorbs, reflects, and scatters a fraction of the incoming sunlight, so a beam that travels through 6 air masses has lost far more energy to atmospheric absorption and scattering than one that travels through just one. This is why the low winter sun not only spreads its energy over a larger area, but also delivers less energy to begin with, having lost more of it to the longer atmospheric path. The interaction of these two effects, geometric spreading and atmospheric absorption, makes winter sunlight doubly weak. The geometric effect reduces the energy per unit area directly in proportion to the angle. The atmospheric effect further reduces the total energy in the beam before it even reaches the surface. Together, They mean that a winter noon in London, which receives sunlight from a sun 16 degrees above the horizon, after traversing nearly 4 air masses of atmosphere, delivers only a tiny fraction of the energy per unit area of a July noon in the same location, when the sun is 63 degrees high and traverses less than 2 air masses. The same sun, the same distance away, provides dramatically different amounts of surface heating, depending solely on the geometry of Earth's tilt. This geometric principle also explains a phenomenon that every person who has used a solar panel or grown plants under artificial lighting knows intuitively. The orientation of a surface toward its light source matters enormously. A solar panel tilted toward the sun captures far more energy than one lying flat when the sun is low in the sky. This is why solar panels in the northern hemisphere are installed tilted southward at an angle roughly equal to the local latitude to maximize the angle of incidence of winter sunlight. It is why greenhouses are designed to maximize south-facing glass area. It is why south-facing slopes in mountain regions are dramatically warmer and ecologically different from north-facing slopes at the same altitude. A south-facing alpine meadow receives sunlight at a steeper angle than the surrounding flat ground or north-facing slopes, effectively experiencing a warmer microclimate than its altitude would suggest. The angle of light is also what creates the dramatic lighting quality that makes winter sunsets and winter landscapes so photographically beautiful. When the sun is low in the sky, its light travels through a much longer atmospheric path, which selectively scatters out the shorter blue wavelengths and allows the longer red and orange wavelengths to reach the surface with reduced competition. This is why winter sunsets are often more intensely colored than summer sunsets, and why the winter noon light has a warm golden quality that photographers prize. The same atmospheric scattering that weakens the energy of winter light also transforms its color, enriching the reds and oranges and giving winter landscapes their characteristic quality of low, warm, raking illumination. The angle of light principle extends beyond Earth and provides a universal rule for understanding how solar heating works on any planet, moon, or surface in the solar system. The equatorial regions of any planet with an axial tilt similar to Earth's will always be warmer than the poles, because they receive sunlight at more consistently vertical angles. The poles will always receive their most solar energy during summer, when this fifth E-tilt brings them into more direct alignment with the sun. The geometry of light and shadow, the cosine rule of irradiance, the relationship between angle and energy density, are the same physical laws everywhere in the universe, shaping the temperature distribution on every surface that receives radiation from a star. Summer's heat is not a single effect, but the product of two separate but mutually reinforcing forces that conspire together to deliver the maximum possible solar energy to the surface. These two forces are the length of the day and the angle of the sun, and at mid to high latitudes in summer, both are working simultaneously at or near their annual maxima. Neither alone would be sufficient to produce the dramatic warmth of a summer heat wave, but together they multiply each other's effects in a way that makes summer heating far more powerful than either factor could achieve alone. Understanding how these two forces combine is to understand the engine of the seasons in its most active state. Consider first the effective day length in isolation. During the summer solstice, at 50 degrees north latitude, the sun is above the horizon for approximately 16 hours. During the winter solstice at the same latitude, the sun is above the horizon for only about 8 hours. This means that in summer, the total time during which solar heating of the surface is possible is exactly twice as long as in winter. Even if the sun were at the same height in the sky during both seasons, the summer day would deliver twice as much total energy to the surface, simply because the sun is present for twice as many hours. Any given square meter of ground has twice as long to absorb solar energy in summer as in winter, and the accumulated heat at the end of a summer day represents this doubled exposure. Now consider the effect of sun angle in isolation. At 50 degrees north latitude on the summer solstice, The sun reaches a noon altitude of about 63.5 degrees above the horizon. On the winter solstice at the same location, the noon sun is only about 16.5 degrees above the horizon. Using the sine function to calculate the energy delivered per unit area relative to the maximum possible, summer delivers about 89% of the maximum energy intensity at noon, while winter delivers only about 28%. This means that at their respective noon peaks, the summer sun is more than 3 times as intense per unit area as the winter sun at the same location. When both effects operate simultaneously, as they do in nature, their combined impact is multiplicative rather than merely additive. To calculate the total daily solar energy delivered to a surface in summer versus winter, we must integrate the instantaneous intensity, which depends on the sun's altitude and varies across the day from 0 at sunrise to maximum at noon and back to 0 at sunset, over the total number of hours the sun is above the horizon. For the summer solstice at 50 degrees north, this integral is roughly 4 to 5 times larger than the corresponding integral for the winter solstice. In other words, a summer day at this latitude delivers approximately 4 to 5 times as much total solar energy to the surface as a winter day, purely because of the combined effect of longer days and a higher sun. This factor of 4 to 5 in daily solar energy input is the primary explanation for why summer is so dramatically warmer than winter at mid-latitudes. The difference is not marginal or subtle. It is a factor of nearly 5 in the fundamental energy input driving the entire thermal system of the atmosphere, land, and ocean surface, even after accounting for the time it takes for this energy difference to manifest as temperature change. The seasonal lag. The underlying driver is this enormous difference in daily solar energy received. The combined effect of day length and sun angle also explains why the length of the day matters so much more for seasonal heating at higher latitudes than at lower ones. At the equator, the sun's altitude varies relatively little across the year, and the day length varies even less. At 60 degrees north latitude, both variables show extreme seasonal swings. Day length varies from about 6 hours in winter to about 18 hours in summer, a factor of 3, while noon sun altitude varies from about 6.5 degrees in winter to about 53.5 degrees in summer. The product of these two effects is enormous at high latitudes, which is why northern cities like Stockholm and Helsinki experience summers that can be genuinely warm despite their high latitudes. The relationship between day length and sun angle is not arbitrary. It follows from the underlying geometry of the axial tilt. When the North Pole is tilted most toward the sun at the summer solstice, both effects are maximized simultaneously. The same tilt that raises the sun highest in the sky also keeps it above the horizon the longest, and when the tilt swings to its winter extreme, both effects are minimized simultaneously. The sun is both at its lowest and above the horizon for the fewest hours. The two factors are not independent variables that happen to coincide. They are different manifestations of the same underlying geometric arrangement, and they therefore reinforce each other as systematically as they are both driven by the same cause. This compounding of solar effects in summer is also what drives many of the secondary effects of the summer season. The abundant solar energy of the summer months is what fuels the explosive growth of vegetation, the high rates of evaporation that load the atmosphere with moisture for summer thunderstorms, the warming of ocean surface waters to temperatures that sustain coral reefs and support the highest marine productivity of the year, and the heating of the land to temperatures that drive the intense convective circulations responsible for summer weather patterns. Every summer thunderstorm, every blooming flower, every barefoot walk on hot sand is powered ultimately by the combined effect of a high sun and a long day, two aspects of the same tilted geometry working together to transfer the maximum possible energy from a distant star to the surface of this planet. In the early 20th century, a Serbian mathematician and astronomer named Milutin Milankovic sat down to calculate something that no one before him had managed to work out in full mathematical detail how the systematic, predictable variations in Earth's orbit and axis change the distribution of solar energy across the planet's surface over tens of thousands of years, and whether these changes could explain the ice ages that geologists had discovered in the rock record. Milankovitch did not have a computer. He had his own formidable mathematical mind, a pencil, and years of dedicated calculation. He produced detailed tables of insolation, the amount of solar radiation reaching different latitudes at different times of year, across hundreds of thousands of years of past time. The pattern he found buried in those tables has become one of the most important theoretical frameworks in all of climate science, and the rhythms he identified carry his name, the Milankovitch cycles. There are three distinct cycles that Milankovitch identified as major drivers of long-term climate change. The first is the eccentricity cycle, which describes the way in which the shape of Earth's orbit around the Sun slowly changes over time. Earth's orbit is currently very nearly circular, with an eccentricity of 0.0167. But over a period of roughly 100,000 years, the gravitational influence of Jupiter and Saturn, the two most massive planets in the solar system, causes the orbit to become more elongated and then return toward circularity. When the orbit is at its most eccentric, the difference in Earth-Sun distance between perihelion and aphelion is substantially larger than it is today, leading to larger differences in solar energy received at those 2 points in the orbit. The eccentricity cycle, with a period of about 100,000 years, is thought to be the dominant cycle in the Ice Age record over the past million years. The second cycle is the obliquity cycle, which describes the slow variation in the tilt of Earth's rotational axis. Currently 23.5 degrees, the tilt oscillates between about 22.1 and 24.5 degrees over a period of roughly 41,000 years. When the tilt is at its maximum, the seasonal contrast is greatest. Summers are hotter and winters are colder at all latitudes above the equator. When the tilt is at its minimum, seasons are more muted. The obliquity cycle does not change the total amount of solar energy Earth receives over the course of a year, but it changes how that energy is distributed across latitudes and seasons. Greater obliquity sends more energy to the polar regions in summer and less in winter. Smaller obliquity does the reverse. The third cycle, and the one with the most complex structure, is the precession cycle, which describes the slow wobble of Earth's rotational axis in space, like the wobble of a spinning top that is beginning to slow down. Earth's axis traces a complete circle in space over a period of about 26,000 years, which means that the direction in which the North Pole points, currently toward Polaris, gradually changes, sweeping through all the stars of the northern celestial hemisphere over this period. More importantly for climate, the precession cycle changes the relationship between the seasons A and Earth's position in its orbit. Currently, the northern hemisphere winter solstice coincides approximately with perihelion, when Earth is closest to the Sun. About 11,000 years ago, it was the other way around. The northern hemisphere summer solstice occurred near perihelion, giving northern hemisphere summers a slight boost in solar energy. The way these three cycles interact to drive ice ages is complex and is still actively debated by climate scientists, but the broad outlines are reasonably well understood. The growth and shrinkage of continental ice sheets depends primarily on what happens to solar energy during summer at high northern latitudes. Because this is where the large continental ice sheets of past ice ages, centered over North America and Scandinavia, accumulated and melted. For an ice sheet to grow, it is not enough for winters to be cold. Winters at high latitudes are always cold enough for abundant snow. What matters is whether the summer is warm enough to melt the snow and ice that accumulated during winter. If summers are cool, last winter's snow can survive and accumulate, eventually compressing into glacial ice. If summers are warm, ice melts and the sheet retreats. The Milankovitch hypothesis therefore predicts that ice ages should be most extensive when the combination of orbital and axial parameters produces the coolest summers at high northern latitudes. This typically occurs when the eccentricity is high, putting northern hemisphere summer near aphelion. When the obliquity is low, reducing the summer energy input at high latitudes. And when the precession cycle has summer solstice occurring near aphelion rather than perihelion. The record preserved in ocean sediments and ice cores over the past several million years shows a pattern of glacial interglacial cycles that closely matches the pacing predicted by Milankovich's calculations. Dominant 100,000-year cycle of ice ages over the past million years corresponds to the eccentricity cycle. An earlier phase of more rapid 41,000-year cycles corresponds to the obliquity cycle. The agreement between the mathematical predictions and the geological record is striking and has convinced the majority of climate scientists that Milankovitch cycles are the fundamental pacemaker of the ice ages. The implications of Milankovitch cycles for the current climate are of more than theoretical interest. We are currently in an interglacial period, the Holocene, which began about 11,700 years ago, when the ice sheets of the last glaciation retreated. Based on the Milankovitch cycles alone, we might expect a current interglacial to continue for many thousands more years before conditions favorable to renewed glaciation recur. However, human emissions of greenhouse gases have added a powerful new forcing to the climate system that has no analog in previous interglacials, and climate scientists broadly agree that the current warming trajectory will prevent the natural Milankovitch-driven cooling for an extended period. The Milankovitch cycles, which have governed the rhythm of ice ages for millions of years, are for the first time in Earth's history being modulated by the activities of a single species. 12. The Moon's role, guardian of Earth's stable tilt. It is one of the less commonly appreciated facts about our planet that the familiar, reliable seasons we experience, the predictable rhythm of summer and winter that has shaped all of life on Earth, are in part a consequence of a violent accident that occurred roughly 4.5 billion years ago. The event in question is the giant impact hypothesis, the widely accepted theory that early in Earth's history a Mars-sized body called Theia collided with the proto-Earth at a glancing angle, blasting material from both objects into space. This debris gradually coalesced into the Moon. The Moon that formed from this catastrophic collision is not just a beautiful object in the night sky or the driver of ocean tides. It is, according to the best models we have of Earth's rotational dynamics, the primary reason that our planet's axial tilt has remained stable within a narrow range for billions of years, and therefore a major reason that the seasons have been predictable rather than chaotic across the timescale of life's evolution. The stability of Earth's axial tilt is not guaranteed by simple orbital mechanics. Earth is subject to gravitational torques from the Sun, the Moon, and the other planets, particularly the large outer planets Jupiter and Saturn. These torques have the potential to cause the axis to precess and wobble, and if they were to resonate with the natural frequencies of Earth's orbital parameters, they could drive large and rapid changes in the tilt. Computer simulations of Earth's long-term rotational dynamics, conducted in the 1990s by French astronomers Jacques Lascar and colleagues, showed that without the Moon, the gravitational perturbations from other planets would cause Earth's axial tilt to undergo chaotic variations over millions of years, potentially ranging from nearly 0 degrees to more than 85 degrees. Such extreme variations would produce climate changes of extraordinary magnitude, far exceeding the ice ages and warm periods driven by the relatively modest Milankovitch cycles. The Moon prevents this chaotic behavior through a phenomenon called orbital resonance and the stabilization of the precession frequency. The Moon's gravitational pull on Earth's equatorial bulge, the slight flattening of Earth at the equator due to its rotation, produces a torque that causes the rotational axis to precess, to trace its slow 26,000-year circle in space. This precession frequency is set primarily by the Moon's orbital influence. Critically, this Moon-determined precession frequency keeps Earth out of resonance with the dominant gravitational perturbations from Jupiter and Saturn, which would otherwise drive large amplitude, chaotic oscillations, remove the Moon, and the precession frequency shifts, bringing it into resonance with the planetary perturbations and opening the door to the chaotic tilt variations that the simulations reveal. The climate consequences of a moonless Earth with chaotic axial tilt are difficult to imagine in their full scope. At near zero tilt, Earth would have essentially no seasons at all. The equator would be a permanent desert, the tropics a narrow warm band, and the polar regions locked in permanent cold. At extreme tilts approaching 90 degrees, the seasons would be violent beyond anything in Earth's current experience. The polar regions would alternately face the sun continuously for months, heating to temperatures that no currently existing polar ecosystem could survive, then plunge into months of absolute darkness and cold. Life on such a world might persist, but it would face adaptation challenges far more extreme than those imposed by the relatively modest 2.4-degree range of tilt variation that the Moon allows. The complex multicellular life that has evolved on Earth over the past several hundred million years might well not have had the environmental stability required to develop. The Moon's stabilizing role is a dramatic example of a broader principle in planetary science. The habitability of a planet is not determined solely by its distance from its star and the composition of its atmosphere, but also by the detailed dynamics of its orbital environment and the presence or absence of large moons and neighboring planets that can either stabilize or destabilize its climate. Earth's orbital environment is unusually benign in several respects. The presence of a large moon maintains tilt stability. The existence of Jupiter as the dominant mass in the outer solar system provides a measure of shielding against impact threats from the outer solar system, while also providing the gravitational perturbations that drive the eccentricity cycle. The near circularity of Earth's orbit keeps the variation in Earth-Sun distance modest. Whether all of these favorable conditions are rare in a galaxy or are commonly found around Sun-like stars is one of the central questions of the search for habitable exoplanets. The Moon is also the driver of another seasonally relevant phenomenon: the tides. The tidal forces exerted by the Moon on Earth's oceans produce the twice-daily rhythm of high and low tides at coastal locations around the world, and these tides show their own seasonal variation that interacts with the astronomical seasons in complex ways. The highest tides of the year, the spring tides, occur at new moon and full moon, when the Sun, Earth, and Moon are aligned, and the gravitational poles of the Sun and Moon add together. The timing of these highest spring tides, relative to the seasons, depends on the relationship between the lunar orbit and Earth's orbital path around the Sun, producing a complex calendar of tidal extremes that coastal communities around the world have used for navigation, fishing, and agriculture for thousands of years. The relationship between the Moon and the seasons reaches deeply into the history of timekeeping and the cultural organization of human life. As discussed in the context of lunar calendars, the Moon's monthly cycle provided humanity's first practical unit of time measurement, and the interaction between the lunar month of 29.5 days and the solar year of 365.25 days generates the complex, beautiful mathematics of lunisolar calendars that have governed human timekeeping in many traditions. The Moon is simultaneously a stabilizer of Earth's long-term climate, a driver of short-term tidal rhythms, and a timekeeper of monthly cycles, all while remaining a beautiful invisible presence in the night sky that has inspired human imagination and wonder since the first eyes looked upward. Of all the planets in our solar system, Mars is the one most often discussed as a potential future home for humanity, and one of the reasons for this is that, on the surface at least, it seems somewhat familiar. It has a day almost exactly as long as Earth's, 24 hours and 37 minutes. It has an axial tilt of 25.2 degrees, close enough to Earth's 23.5 degrees that it experiences recognizable seasons with summer and winter at both poles, spring warmings and autumn coolings that would seem almost intuitive to an Earth-born observer. Its polar regions carry ice caps that grow and shrink with the seasons. Dust storms sweep across the landscape in patterns that vary with the season. The planet is a world with a seasonal rhythm, organized by the same fundamental mechanism as Earth's, an axial tilt maintaining its orientation as the planet orbits the sun. But the details of Martian seasons reveal a world where familiar mechanisms produce profoundly unfamiliar outcomes. The most immediately striking difference between Martian and earthly seasons is their duration. Mars takes 687 Earth days to complete one orbit around the sun, nearly twice as long as Earth's year. A Martian year is therefore 687 Earth days, roughly 1.88 Earth years, and the seasons it contains are proportionally longer. A Martian summer lasts not 3 months, but more than 5. A Martian winter stretches on for over 5 months as well. The total seasonal cycle that an organism adapted to the Martian seasons would experience is twice as long as the one familiar to any Earth-dwelling creature, with summers that extend across most of the Earth calendar year, and winters that follow with similar endurance. Mars also has a significantly more eccentric orbit than Earth. While Earth's orbital eccentricity is 0.017, Mars's is 0.093, nearly 6 times greater. This means that the difference in Mars-Sun distance between perihelion and aphelion is much larger than the corresponding difference for Earth. At perihelion, Mars is about 207 million kilometers from the Sun. At aphelion, it is about 249 million kilometers away. This 20% variation in distance produces a variation in solar energy received of about 40%, a much larger effect than Earth's 7% variation. The result is that on Mars, unlike on Earth, the orbital eccentricity makes a significant contribution to the character of the seasons in ways that compound or counteract the axial tilt effect. Currently, Mars's perihelion occurs near the southern summer solstice. This means that when the southern hemisphere is having its summer, Mars is also closest to the Sun, giving the southern summer a boost in solar energy from the eccentricity effect. Southern Martian summers are therefore relatively hot and intense. Meanwhile, the northern summer occurs near aphelion, when Mars is farthest from the Sun, making northern summers relatively cool and mild. Conversely, southern winters occur near aphelion and are therefore particularly cold and long, while northern winters are somewhat moderated by the perihelion effect. This asymmetry between the two hemispheres, absent on Earth where the eccentricity effect is too small to matter much, gives Mars a distinctly lopsided seasonal pattern in which the two hemispheres experience qualitatively different seasonal extremes. The consequences of this asymmetry are most dramatically visible in the behavior of the polar ice caps. The Martian poles are covered not by water ice, as Earth's poles primarily are, but by a mixture of water ice and carbon dioxide ice, the latter of which forms and evaporates seasonally. In winter, carbon dioxide from the atmosphere freezes out directly onto the polar surface, forming a seasonal cap of dry ice that can reach thicknesses of a meter or more. In summer, this seasonal cap sublimates back into the atmosphere, dramatically changing the atmospheric pressure of Mars as a whole. In the depths of southern winter, enough atmospheric carbon dioxide freezes out at the South Pole that Mars's atmospheric pressure drops measurably planet-wide. This remarkable phenomenon has no parallel on Earth, where the water cycle redistributes water between liquid vapor and solid states, without significantly changing the total atmospheric mass. The seasonal temperature range on Mars is extreme by Earth standards. At the equator, Martian temperatures can reach a relatively mild 20 degrees Celsius on a summer afternoon, but plummet to minus 80 degrees Celsius on the same night, as the thin atmosphere loses heat rapidly by radiation to space. At the poles in winter, temperatures can fall below minus 125 degrees Celsius, cold enough for carbon dioxide to freeze. The thin Martian atmosphere, roughly 1% of Earth's atmosphere pressure at sea level, provides almost no thermal buffering or heat retention, so the diurnal and seasonal temperature swings are far more extreme than those of any location on Earth. The seasonal lag that smooths Earth's seasons is minimal on Mars, because there are no oceans and very little atmosphere to store and slowly release heat across the seasonal cycle. Perhaps the most spectacular seasonal phenomenon on Mars is the global dust storm. Every few Martian years, particularly during southern hemisphere summer, when Mars is near perihelion and solar heating is mass, intense dust storms that begin as regional events can grow to cover the entire planet in a thick cloud of suspended particles, blocking out most of the sunlight reaching the surface for weeks or even months. These global dust storms temporarily collapse the normal seasonal temperature gradients across the planet, warming the atmosphere by absorbing sunlight high up while cooling the surface beneath the dust layer. The storms eventually subside as dust settles, but they can dramatically alter the character of the southern summer season in any given Martian year. The Mars rover Opportunity, which operated for nearly 15 Earth years, was eventually killed by a global dust storm in 2018, when the prolonged reduction in sunlight depleted its solar panels below the level needed to survive the Martian winter. For any future human presence on Mars, the seasonal cycle will be a fundamental constraint on life and operations. The long Martian year means that any sustained human presence would need to be designed for survival through extended seasonal extremes, including the intense cold of polar winters, the dust storm season of the southern summer, and the profound challenge of growing food in a seasonal cycle twice as long as Earth's, with daylight levels reduced to about 43% of Earth's by Mars's greater distance from the Sun. If the seasons of Earth seem dramatic, with their swings from summer heat to winter cold, their long polar nights and midnight suns, consider what it would mean to live on a planet where the axial tilt is not 23.5 degrees, but 97.77 degrees. A planet so tipped on its side that it rolls around its orbit like a ball, rather than spinning upright like a top. This is Uranus, the seventh planet from the Sun, and its extraordinary axial tilt produces seasonal conditions so extreme that they are difficult to conceptualize using any framework built from light. Experience of Earth's relatively modest seasonal variation. On Uranus, one pole spends an entire season facing the Sun continuously while the other sits in unbroken darkness, and then they swap. The seasons are not 4 distinct phases of a year, but 2 enormous alternating hemispheres of light and darkness, each lasting roughly 21 Earth years, separated by transitional periods of more balanced illumination. Uranus experiences the most extreme seasonal cycle of any planet in the solar system, and it is all the consequence of that single extraordinary number, 97.77 degrees of tilt. The origin of Uranus's extreme tilt is believed to be an ancient catastrophic collision with a large object early in the solar system's history, similar to the giant impact that created Earth's moon, but far more violent in its effects on the planet's rotation. The collision must have been large enough and oriented in just the right way to knock Uranus almost completely onto its side, and the planet has remained in that orientation for the 4.5 billion years since. At 97.77 degrees of tilt, the planet's axis is actually more than 90 degrees from the perpendicular, which technically means it is rotating in the retrograde direction relative to its orbital motion. Its north pole, as defined by the direction of its rotation, points southward in the solar system's conventional frame of reference. The seasonal consequences of this extreme tilt are unlike anything in the experience of an Earth-bound observer. Uranus takes 84 Earth years to complete one orbit around the Sun. With a tilt of 97.77 degrees, the solstice geometry on Uranus is almost the exact opposite of what we experience on Earth. At the Uranian summer solstice in the northern hemisphere, the North Pole points almost directly at the Sun. For roughly 21 years centered on this solstice, the entire North Polar region receives continuous sunlight, while the South Polar region is locked in continuous darkness. The pattern then gradually shifts as Uranus continues around its orbit, and over the next 21 years, the planet's equatorial regions and then its South Polar region come into more direct sunlight as the geometry slowly transitions toward the other solstice. The nature of this extreme polar illumination creates a profound puzzle in planetary science that has not yet been fully resolved, with one pole receiving direct sunlight for 21 years and the other sitting in complete darkness for the same period. One would expect the sunlit pole to become dramatically warmer than the dark pole. The sunlit pole should accumulate an enormous amount of solar energy over 2 decades of continuous summer, while the dark pole should radiate heat to space continuously for 21 years and become correspondingly cold. Yet Voyager 2, the only spacecraft to have visited Uranus when it flew past in 1986, found that the temperature difference between the two poles was much smaller than expected. The atmosphere of Uranus appeared to be distributing heat from the sunlit to the dark pole, with surprising efficiency, moderating the temperature contrast between the two hemispheres despite the extraordinary difference in solar illumination they were receiving. Uranus also has one of the most puzzling internal heat problems in planetary science. Jupiter, Saturn, and Neptune all radiate significantly more heat from their interiors than they receive from the Sun, indicating that they have warm interiors losing heat to space. Uranus, despite being similar in size and composition to Neptune, radiates almost no internal heat. Its internal heat flux is essentially zero, making it the only giant planet in the solar system that is not losing heat from its interior. The reason for this anomaly is unknown, but one hypothesis connects it to the extreme tilt, the unusual orientation of Uranus's magnetic field, which is also highly tilted relative to the rotation axis and dramatically offset from the planet's center, may prevent efficient convection within the planet's interior, trapping whatever internal heat exists, rather than allowing it to escape to the surface. The moons of Uranus, of which 27 have been discovered so far, orbit in the same tilted plane as the planet's equator, meaning they too experience the extreme seasonal illumination of the Uranian system. When the North Pole is pointing toward the Sun, the moons orbiting in Uranus's equatorial plane are illuminated from almost directly above their orbital plane, and they can pass through long periods of continuous sunlight or continuous darkness depending on their orbital orientation relative to the Sun. The complex seasonal light environment of the Uranian moons makes them some of the most unusual objects in the solar system from a seasonal perspective. The atmosphere of Uranus itself is seasonally active in ways that Earth-based telescopes and the Hubble Space Telescopes have documented over the decades since Voyager 2's visit. As Uranus has moved through its long orbit since 1986, the illumination geometry of its atmosphere has changed, and astronomers have observed corresponding changes in cloud patterns, atmospheric dynamics, and the brightness of the polar regions. The Uranian spring and autumn equinoxes, when the Sun is above the equator and both hemispheres receive equal illumination, are expected to be times of maximus activity, as the thermal gradient between the poles and the equator is most dynamic during these transitional periods. The 2007 equinox, when the Sun crossed Uranus's equator, was indeed associated with unusually prominent storm systems in the planet's atmosphere, suggesting that the seasonal transition is dynamical. Significant. Uranus reminds us that the seasons we experience on Earth, while profound in their consequences for life, are one relatively modest point on the vast spectrum of seasonal regimes that the physics of axial tilt and orbital mechanics can produce. A 23.5-degree tilt gives us the drama of 4 distinct seasons cycling through a single year. A 97.77-degree tilt gives a world where each season lasts 2 decades and alternates between poles of total illumination and total darkness. The same physics, the same laws of gravity and orbital mechanics, the same relationship between axial tilt and the angle of incoming sunlight, operating at different scales and under different initial conditions, produces seasonal worlds as different from each other as any 2 environments could be. Every autumn in North America, a phenomenon begins that has no parallel for scale, precision, and biological elegance anywhere in the natural world. From breeding grounds across the Arctic tundra and the boreal forests of Canada, hundreds of millions of individual birds begin moving south. Warblers, thrushes, shorebirds, raptors, waterfowl, Species that have spent the summer exploiting the abundant food of the northern summer begin to respond to the shortening days and cooling temperatures, activating ancient navigational programs encoded in their neurology and departing on journeys that will carry many of them across thousands of kilometers of ocean and continent to wintering grounds in the tropics or the southern hemisphere. They follow the warmth and the food, chasing the productive season southward as Earth's axial tilt tilts the northern hemisphere away from the sun. This is the miracle of bird migration, the most visible and dramatic biological expression of the seasonal cycle. Migration, in the broad biological sense, is a response to the seasonal availability of resources. The fundamental driver is simple. At high latitudes, the summer produces an extraordinary abundance of food, driven by the long days and intense sunlight that stimulate enormous productivity in terrestrial and aquatic ecosystems. Insects hatch in enormous numbers, fish spawn in rivers and coastal waters, plant growth explodes, and the food resources available to small animals are at their annual peak. But this abundance is temporary. As the seasons change and the days shorten, the cold arrives. Insects disappear, plants die back, and the northern landscape becomes a challenging environment for animals that have exploited its summer richness. Those that can move south do so, tracking the productive season as it migrates with the changing angle of the Earth. The evolutionary logic of migration is essentially an arbitrage. The migratory animal can exploit two different seasonal resources that a non-migratory animal cannot simultaneously access. A warbler that breeds in Canada and winters in the Amazon is essentially having two summers, exploiting the northern summer for breeding and the southern tropics for wintering. Where the dry season, in many regions, still supports abundant insect populations, the cost is the enormous energy expenditure of the migration itself, the danger of too long journeys each year, and the navigational challenges of crossing vast distances of unfamiliar landscape. For the many species that undertake these journeys, the benefit in terms of access to seasonal food abundance and suitable breeding conditions outweighs these costs, as demonstrated by the fact that migratory strategies have evolved independently in many different animal groups. The navigational abilities that migratory animals use are among the most remarkable biological feats known to science. Birds navigate using a multimodal system that includes stellar cues, reading the pattern of stars in the night sky, to determine compass direction, magnetic field sensing, detecting the direction and inclination of Earth's magnetic field through a poorly understood mechanism that may involve quantum mechanical processes in molecules in the eye, visual landmarks, particularly in familiar areas near the breeding and wintering grounds, the position of the sun during the day compensated by an internal clock, infrasound, the very low-frequency sound waves produced by geographical features like mountains and coastlines that can be detected from vast distances, and olfactory cues in some species. This multimodal navigation system provides redundancy, so that if one cue is unavailable, others can compensate. The timing of migration is calibrated to the seasonal cycle with extraordinary precision, and it is primarily controlled by day length rather than by temperature. This is a critical distinction. A bird that waited until temperatures fell before beginning its autumn migration would often wait too long and miss the window for safe departure. Instead, migratory birds use the shortening days of late summer and early autumn as their primary migration trigger, beginning the physiological preparation for migration, including hyperphagia, the dramatic increase in food intake that deposits the fat reserves needed for long flights, weeks before temperatures have changed substantially. This day-length sensitivity ensures that the birds depart on a schedule that has been optimized by natural selection over millions of years of migration, not an opportunistic response to weather conditions. The distances covered by migratory animals are staggering. The bar-tailed godwit, a shorebird that breeds in Alaska, makes the longest non-stop flight of any bird, flying continuously for up to 9 days across the Pacific Ocean from Alaska to New Zealand, a distance of about 11,000 kilometers, without landing, drinking, or eating. During this flight, the bird burns virtually all of its fat reserves and even breaks down its own muscle and organ tissue for fuel, shrinking its digestive organs, which are useless during the flight, to reduce weight and redirect energy to the muscles and heart. When it arrives in New Zealand for the southern summer, it is emaciated and exhausted, but it has successfully tracked the productive season from one end of the Pacific to the other. Marine mammals also migrate with the seasons in patterns that are less visible, but no less extraordinary than bird migrations. Humpback whales breed in warm tropical waters in winter and migrate to polar feeding grounds in summer to exploit the extraordinary productivity of polar seas during the brief period of intense phytoplankton growth that follows the polar summer. Individual humpback whales have been documented making round trips of more than 25,000 kilometers in a single year, among the longest migrations of any mammal. The timing of this migration is coordinated with the seasonal cycle of polar productivity, which in turn is driven by the same axial tilt and seasonal light dynamics that drive all of Earth's seasonal phenomena. Migration is ultimately a biological technology for time travel, a way of being in the right place at the right time across a seasonal cycle where the right place changes continuously. It is the most direct expression in animal behavior of the fact that Earth's axial tilt distributes solar energy unevenly across the year, creating a world where abundance and scarcity, warmth and cold, light and darkness move across the landscape in a predictable annual rhythm. Every migratory animal is in some sense chasing the summer, following the productive season around a tilted planet, exploiting the geometry of a 23.5-degree lean to extract the maximum possible benefit from a year that offers its greatest gifts only to those willing to move. In a greenhouse in the 1920s, two American scientists named Whitman Garner and Henry Allard made a discovery that would transform agricultural science and reveal one of the most elegant biological sensory systems ever described. They had been puzzling over a mutant strain of tobacco plant that refused to flower on the normal schedule, continuing to grow vegetatively while surrounding plants were producing flowers and seeds. When they moved the plants into a shed and controlled the hours of light they received each day, they found that the plants would flower only when the days were short enough and the nights long enough. When they artificially shortened the day or lengthened the night, flowering occurred. When they kept the plants under long days, flowering was suppressed indefinitely. They named this response photoperiodism, from the Greek words for light and period, and in doing so they opened a new chapter in our understanding of how living organisms track the seasons. Photoperiodism is the ability of an organism to detect and respond to the relative lengths of day and night, using this information to time biological events to the appropriate season of the year. It is found not just in plants, but also in insects, fish, birds, and mammals, and it underlies the seasonal timing of an enormous range of biological events, including flowering, fruiting, seed dormancy, leaf fall, hibernation, breeding, migration, and molt. In all of these cases, the organism is using day length, or more precisely night length, as a reliable proxy for the time of year, allowing it to time its biological activities to coincide with seasonal conditions that favor their success. Plants that flower only when the night exceeds a critical minimum length are called short-day plants, a term that reflects the original, slightly misleading description that focuses on day length rather than night length. Classic short-day plants include chrysanthemums, poinsettias, soybeans, and the tobacco plants that Garner and Allard originally studied. These plants flower in autumn, when the nights have lengthened beyond their critical threshold. Plants that flower only when the night is shorter than a critical maximum are called long-day plants. These flower in spring and summer, when the short nights of the longer days signal that summer conditions have arrived. Long-day plants include wheat, barley, spinach, and many common vegetables. Day-neutral plants flower regardless of day length, responsive primarily to temperature or other cues rather than to photoperiod. The mechanism through which plants detect night length is based on a remarkable light-sensitive protein called phytochrome. Phytochrome exists in two interconvertible forms: Pri, which absorbs red light and is the form that accumulates in the dark, and Par, which absorbs far red light and is rapidly converted from Pri in daylight. During the day, sunlight converts most of the phytochrome in a plant to the Pr form. After sunset, Pr form gradually converts back to Pri through a process that requires a specific amount of time to complete. The plant effectively uses the ratio of Pran to Pa shifts as a molecular clock, measuring how long the night has been by how much Phr has reverted to Pri. A short night does not give enough time for full conversion. A long night allows more complete conversion. The plant compares this measure of night length to a genetically encoded threshold, and if the threshold is exceeded or not exceeded, depending on the type of plant, the signal to initiate flowering is given or withheld. The critical experiment that proved it was night length rather than day length that mattered was beautifully simple. Garner and Allard, and later other researchers, showed that if a long night was interrupted by a brief flash of light in the middle, it had the same effect on flowering as a short night. Short day plants failed to flower and long day plants bloomed. The plants were measuring the duration of uninterrupted darkness, not the total amount of light received per day. This finding has a directly practical application in horticulture. Florists can manipulate the flowering of photoperiodically sensitive plants, like chrysanthemums and poinsettias, by exposing them to brief flashes of light in the middle of the night, resetting the night length clock, and controlling when the plants flower for commercial purposes. A single brief pulse of light is enough to convince a plant that the night has ended and begun again, preventing the accumulation of the uninterrupted darkness needed to trigger flowering. The agricultural significance of photoperiodism is profound. Many of the world's most important food crops are strongly photoperiod sensitive, and their geographical range is limited by the latitudinal variation in day length. Soybeans, for instance, are originally short-day plants adapted to specific latitudes, varieties bred for use at low latitudes, where the days are relatively short year-round, flower too quickly when grown at high latitudes where summer days are much longer, producing small plants with poor yields before the growing season is over. Plant breeders have spent decades selecting for photoperiod-insensitive varieties of soybeans, wheat, rice, and other crops that can be grown across a wider range of latitudes, a process that has been essential to the geographical expansion of agriculture into higher latitudes over the past century. The interaction between pietet, photoperiodism, and the seasonal temperature cycle is complex and creates an important biological phenomenon known as phenological mismatch, which is increasingly recognized as a significant consequence of climate change. Many plant species use a combination of photoperiod and temperature cues to time their flowering, requiring both a minimum night length and a certain number of warm days before they commit to flower. As climate warming shifts the temperature component of this timing signal earlier in the year, some plant species are flowering earlier while others, whose photoperiod requirement is fixed, cannot advance their flowering regardless of temperature. The result is a growing mismatch in the timing of flowers and the pollinators that depend on them, a disruption of the finely tuned seasonal synchronies that have evolved over millions of years of co-adaptation between plants and their biological partners. Long before writing, before mathematics as a formal discipline, before any of the instruments we associate with scientific measurement, human beings were building some of the most precisely oriented structures in human history across every inhabited continent. And over a span of thousands of years, ancient cultures erected standing stones, circular monuments, burial mounds, and temple complexes whose alignments with the rising or setting of the sun on specific days of the year were so exact that they could only have been achieved through generations of careful observation and sophisticated understanding of the sun's seasonal movements. These structures were not accidents or coincidences. They were deliberate astronomical instruments, solar calendars built from stone that allowed their builders to mark the turning points of the seasonal cycle with a precision that served agricultural, ritual, and social purposes. of the highest importance to their communities. The most famous of these monuments is Stonehenge, on Salisbury Plain in southern England. The monument we see today is the result of multiple phases of construction spanning roughly 1,500 years, from around 3000 BCE to about 1500 BCE. In its current form, the most well-known alignment is the orientation of the main axis of the monument toward the northeast, in the direction of the summer solstice, sunrise. On the morning of the summer solstice, the sun rises over the heel stone, a large unshaped sandstone monolith standing outside the main circle, and its light shines directly into the center of the monument along the main axis. This alignment is precise to within a fraction of a degree, and is clearly intentional. The monument is also aligned with the winter solstice sunset in the opposite direction. Looking from the center toward the southwest on the winter solstice, the sun sets between two of the large trilithon stones, the pairs of upright stones supporting horizontal lintels that form the innermost ring of the monument. Stonehenge is remarkable not just for its astronomical precision, but for the scale of the social effort required to build it. The largest stones, the sarsen megaliths that form the outer circle, and the trilithons, weigh up to 25 tons, and were transported from a quarry about 25 kilometers away. The bluestones, a smaller set of megaliths used in earlier and later phases of construction, came from the Preseli Hills in Wales, about 250 kilometers away. Moving these stones using only human and animal muscle, ropes, wooden sledges, and rollers across rivers and over rough terrain required a level of social organization, collective labor mobilization, and long-term planning that speaks to the extraordinary importance of the seasonal calendar to the people who built Stonehenge. They were building not just a monument, but a permanent infrastructure for track. Ingi, the year. Newgrange in Ireland, constructed around 3200 BCE, is even older than Stonehenge and is considered one of the finest examples of megalithic solar architecture in the world. The mound contains a cruciform chamber accessed by a narrow passage about 19 meters long. Above the entrance, a precisely engineered opening called a roof box is positioned so that at the winter solstice sunrise, a beam of light enters the roof box and travels the full length of the passage to illuminate the back wall of the inner chamber for about 17 minutes. This alignment is accurate to within a degree and is clearly the result of sophisticated astronomical observation over many years to determine the exact direction of the winter solstice sunrise at this latitude. The winter solstice alignment of Newgrange is particularly significant because it suggests that the builders were marking the moment of the sun's return at the darkest time of year, celebrating the turning point from which the light would begin to grow. On the other side of the world, the ancient Maya civilization of Mesoamerica developed one of the most sophisticated astronomical calendar systems in human history, built around precise observation of the movements of the sun, moon, and Venus across the sky. The Maya long count calendar, which famously marked a major calendrical cycle completion in December 2012, was just one of several interlocking calendar systems the Maya used. The Hab, or solar calendar, had 365 days and 18 months of 20 days, plus a 5-day intercalary period. Closely tracking the tropical year, many Maya temples and buildings were oriented to specific astronomical alignments, including the position of the sun at the equinoxes and solstices. The Pyramid of Kukulkan at Chichen Itza, also called El Castillo, is designed so that at the spring and autumn equinoxes, the play of light and shadow on its sty, rockcase creates the illusion of a serpent undulating down the steps as the sun moves through the afternoon sky, a visual effect that draws tens of thousands of visitors to the site on each equinox. The tradition of astronomically aligned religious architecture continued well into historical times across many cultures. The great temples of ancient Egypt were systematically oriented to celestial phenomena. The main axis of the Temple of Amun at Karnak is aligned with the winter solstice sunrise. The Abu Simbel Temple, built by Ramesses II, is aligned so that the rising sun illuminates the inner sanctuary and falls on the statues of the gods there on two specific days of the year, February 22nd and October 22nd, believed to correspond to Ramesses II's birthday and coronation day. These alignments required the same kind of patient astronomical babser, and they served the same fundamental purpose, connecting the rhythms of human religious and political life to the cosmic rhythms of the solar cycle. The common thread across all of these astronomical monuments is the recognition, embedded in stone and lasting for millennia, that the seasonal turning points of the year are events of the highest significance to human life and human society. For agricultural peoples dependent on knowing when to plant and harvest, for communities whose food security depended on accurate tracking of the seasons, for societies whose religious worldview placed the sun and its movements at the center of divine order, the precise marking of solstices and equinoxes was not an academic exercise, but a practical and spiritual necessity. The stone calendars of the ancient world are monuments to the depth of humanity's attention to the astronomical machinery that governs the seasons. In the Latin language, two words were joined together to describe one of the most significant astronomical phenomena in the annual calendar: sol, meaning the sun, and sister, meaning to stand still or to stop. Sol sister, solstice. The name captures with beautiful precision the observational reality of the phenomenon. At the solstice, the sun's daily movement along the horizon, its progressive journey from one extreme to the other across the months, comes to a halt. The sunrise point on the horizon, which has been marching steadily north from the December solstice through the months of winter and spring, stops its northward march at the June solstice and pauses before beginning its return journey south. To a careful observer watching the horizon each morning or evening and marking where the sun rises and sets, the standstill of the sun at the solstice would be unmistakable, a pause in the cosmic order before the great reversal begins. The Latin name is not a metaphor or an exaggeration. It is a description of what you actually see. The apparent motion of the sunrise and sunset points along the horizon is a direct consequence of Earth's axial tilt and its orbit around the sun. At the March equinox, the sun rises due east and sets due west everywhere on Earth. As the weeks pass and the northern hemisphere tilts progressively more toward the sunrise point shifts northward along the eastern horizon day by day until it reaches its northernmost extreme at the June solstice. If you live at 50 degrees north latitude, the June solstice sunrise occurs about 40 degrees north of due east, well into the northeastern quadrant of the horizon. After the solstice, the sunrise point begins its slow return southward, reaching due east again at the September equinox and continuing to its southernmost extreme at the December solstice, rising about 40 degrees south of due east, well into the southeastern quadrant. The rate at which the sunrise point moves along the horizon varies across the year in a way that directly explains the apparent standstill at the solstice. Near the equinoxes, the rate of change is at its maximum. The sunrise point moves several tenths of a degree per day, a change large enough to be noticeable from one week to the next if you are watching carefully. Near the solstices, the rate of change approaches zero. In the days immediately around the solstice, the sunrise point moves so slowly that it is impossible to detect any shift from one day to the next. The sun truly appears to have stopped at the horizon. Then, equally imperceptibly at first, the motion resumes in the opposite direction. This is the phenomenon encoded in the Latin name, the standing still of the sun, and it is a real observational effect that anyone can verify by watching and recording sunrise positions over the weeks around a solstice. The cultural and mythological interpretation of this standstill across human history has been remarkably consistent. The solstice is a time of cosmic crisis and cosmic renewal. The sun pauses, as if uncertain whether it will return. Prayers, sacrifices, and rituals are offered to ensure its return, and when it does turn back, joy and celebration follow. In northern cultures, where the winter solstice marks the end of the long darkening of the days and the beginning of the return of light. This cosmic drama was felt with particular intensity. The winter solstice was a time of profound religious significance across the pre-Christian cultures of Europe, marking the death and rebirth of the solar deity and the promise of spring and warmth to come. The Norse celebration of Yule, which takes its name from a word whose ultimate etymology is uncertain, but may be related to words meaning wheel or turning, was centered on the winter solstice and the return of the sun. Large Yule logs were burned for multiple days, the fire symbolizing the warmth and light that would return with the sun. Feasting, drinking, and the telling of stories around fires were central activities, marking a period of rest and social renewal after the autumn's labor and before the spring's planting. Many of the customs associated with the modern Christmas, including decorated trees, gifts, feasting, and the emphasis on light and fire, are directly inherited from the pre-Christian Yule celebration and its neighboring festivals across northern Europe. The summer solstice, the longest day, has had its own rich tradition of celebration, particularly in the Celtic and later the Christian calendar. Midsummer, the period around the June solstice, was associated in many European traditions with bonfires lit on hilltops to celebrate and strengthen the sun at its peak power. In Scandinavia, Midsummer remains one of the most important popular festivals of the year, celebrated with flower garlands, dancing around maypoles, and bonfires lit through the brief northern night. The Christian feast of St. John the Baptist was placed on June 24th, close to the summer solstice, partly absorbing the celebrations of the pre-Christian Midsummer Festival into the new religious calendar, across cultures that had no direct historical contact with each other. The solstice has been independently recognized as a turning point of cosmic significance and marked with ceremony and celebration. The Iranian New Year Nowruz, discussed elsewhere, falls at the spring equinox rather than the solstice, but the principle is the same. A solar turning point, marked as a moment of cosmic renewal and human celebration. The Inca festival of Inti Raymi, the festival of the sun, was held at the winter solstice in the southern hemisphere, around June 21st, and celebrated the sun god Inti at the moment when the sun was at its northernmost point in thin east sky as seen from Cusco. The solstice was a time for the Inca emperor to make offerings to the sun and pray for its continued beneficence, demonstrating the same fundamental recognition of the solstice as a pivot point in the solar cycle that characterizes solstice celebrations across the entire range of human civilizations. The word solstice itself, carried forward from Latin through the Romance languages and into English, is a small linguistic monument to the human capacity for precise astronomical observation and for naming what is observed with clarity and economy. Solstice, the sun stands still, in those two words, embedded in the most mundane of calendar vocabulary, is the distilled record of countless generations of careful watching, of people standing at the horizon in the days around the solstice and noting, day after day, that the sunrise point was not moving, that something extraordinary and significant was happening in the sky. The sun was pausing, and presently it would turn, and the season would begin its slow reversal, carrying the world once more from one extreme to the other in the ancient, predictable, comforting rhythm of the year. Every year, as the days shorten in autumn, and the light of the northern winter grows thin and sparse, a significant proportion of the population in temperate and high-latitude regions begins to experience a characteristic cluster of symptoms: persistent low mood, profound fatigue, difficulty waking in the morning, increased appetite with specific cravings for carbohydrate-rich foods, withdrawal from social activity, difficulty concentrating, and a general sense of heaviness and diminished energy that seems to lift, as if by magic, when the days begin to lengthen again in spring. These symptoms are not imaginary, not merely the subjective discomfort of people who happen to prefer warm weather, and not simply the reasonable response of anyone to the inconveniences of winter. They are the recognized symptoms of a diagnosable condition called seasonal affective disorder, or SAD, a form of depression that follows the seasonal cycle of light availability as reliably and consistently as the migration of birds or the flowering of spring plants. Seasonal affective disorder was formally identified and named in 1984 by psychiatrist Norman Rosenthal and colleagues at the National Institute of Mental Health, who had observed that a subset of their patients showed a regular pattern of depression in winter, followed by full remission in spring. Rosenthal and his team demonstrated that bright light exposure could alleviate the winter symptoms, providing the first evidence that the condition was directly related to the seasonal reduction in light, rather than to any other feature of winter. Their observation launched decades of research into the neurobiology of seasonal mood changes and the clinical practice of light therapy, which has since become the first-line treatment for SAD. The prevalence of SAD varies dramatically with latitude in a pattern that directly implicates reduced winter sunlight as the cause. In Florida, at about 27 degrees north latitude, roughly 1.4% of the population is estimated to experience SAD. In New Hampshire, at about 43 degrees north, the prevalence rises to about 9.7%, nearly 7 times higher. In the even higher latitudes of Scandinavia and Canada, estimates of SAD-T prevalence range from 10 to 15% or higher. The gradient is clear and consistent. The further north you go, the shorter the winter days, the less sunlight people receive, and the more prevalent seasonal depression becomes. This relationship is among the strongest evidence that reduced light exposure is the primary cause of SAD, rather than other features of winter such as cold temperature, or disrupted holiday routines. The biological mechanism behind SAD is believed to involve primarily the serotonin and melatonin systems, two neurotransmitter and hormone systems whose activity is strongly regulated by light. Serotonin, often called the feel-good neurotransmitter, plays a critical role in mood regulation, and its synthesis and release are stimulated by light exposure. In people who develop SAD, research has found that the serotonin transporter, a protein that clears serotonin from the synaptic cleft and thereby regulates its availability for signaling, is more active in winter than in summer. Higher transporter activity means lower serotonin levels, which is associated with depressed mood, reduced energy, and the other characteristic symptoms of SAD. The reduced light of winter essentially turns up the serotonin transporter, depleting the neurotransmitter that supports mood and energy. Melatonin, the hormone of darkness discussed at length in the context of the night, also plays a role in SAD that is more complex than simple darkness, causing depression. People with SAD tend to have a longer duration of elevated melatonin secretion in winter than in summer, and their melatonin peak occurs somewhat later in the night than in healthy controls. Some researchers believe that this phase delay in the melatonin rhythm creates a mismatch between the body's internal sleep-wake clock and the environmental light-dark cycle that contributes to the characteristic morning fatigue and difficulty waking that SAD sufferers experience. Light therapy, which involves sitting in front of a bright artificial light source for 20 to 30 minutes in the morning, may work partly by advancing the phase of the melatonin rhythm, bringing it back into better alignment with the social and environmental day. The characteristic food cravings of SAD, particularly for carbohydrate-rich and calorie-dense foods, have an interesting evolutionary interpretation. Some researchers have proposed that the seasonal pattern of increased appetite and weight gain in winter represents an atavistic evolutionary heritage from primate ancestors who lived in environments where winter brought food scarcity and where the accumulation of fat reserves in autumn and winter was adaptive. From this perspective, SAD may represent an extreme version of a normal and once adaptive seasonal rhythm of reduced activity, increased appetite, and behavioral withdrawal that was well suited to the conditions of ancestral human environments. But that has become a clinical problem in the modern world where food is abundant year-round and social obligations do not diminish in winter. Light therapy, the primary treatment for SAD, involves daily exposure to bright artificial light, typically at an intensity of 10,000 lux, which is roughly equivalent to being outdoors on a bright but overcast day, for 20 to 30 minutes in the morning. Randomized controlled trials have consistently demonstrated that morning light therapy reduces SAD symptoms more effectively than placebo conditions, such as dim light exposure, and the response to treatment typically occurs within 1 to 2 weeks. The morning timing of light therapy is important. Evening light exposure has been found to be less effective or ineffective, consistent with the hypothesis that the primary mechanism is phase advancing the melatonin rhythm. Antidepressant medications, particularly selective serotonin reuptake inhibitors, are also effective for SAD and are often used in combination with light therapy for more severe cases. The existence of seasonal affective disorder is one of the most directive demonstrations that human biology has not fully adapted to the modern world of controlled indoor temperatures, artificial lighting, and year-round food availability. At some level, our brains still respond to the shortening of winter days by activating ancient circuits that were once adaptive responses to seasonal scarcity. The symptoms of SAD, from lowered mood to increased appetite to social withdrawal, could all be described as components of a behavioral winter dormancy program, a suite of responses to the reduced light and implied scarcity of winter that evolved in our ancestors, but that produces suffering in modern human beings who do not actually need to reduce their activity and increase their caloric intake to survive the cold season. SAD is, in this sense, the mind's slow-motion response to the seasonal dance of Earth around its tilted axis. The Gulf Stream is one of the most powerful rivers on Earth, but it flows entirely within the ocean rather than on land, carrying warm water northward from the tropics, along the eastern coast of North America, and then across the Atlantic toward Europe. It transports an amount of heat energy equivalent to roughly 1,000 times the total electricity generating capacity of the United States. Without it, the climate of northwestern Europe would be dramatically colder than it is today. London, at roughly the same latitude as the Labrador coast of Canada, where sea ice is common in winter, enjoys relatively mild winters because of the warmth delivered to the surrounding ocean and atmosphere by this great oceanic river. The Gulf Stream is not unique. It is part of a global network of ocean currents that continuously redistribute the heat imbalances created by the unequal solar heating of Earth's surface, and these currents interact with the seasonal cycle in ways that are fundamental to understanding regional climates and their seasonal character around the world. The seasonal cycle creates heat imbalances in the ocean because the sun heats different parts of the ocean surface at different times of year. In summer, the ocean surface in the mid-latitudes and subpolar regions absorbs enormous amounts of solar energy, warming the top layer of water significantly. In winter, this stored heat is released back to the atmosphere, moderating the temperature of coastal and maritime regions. The ocean is the planet's primary seasonal heat battery, storing summer heat and releasing it in winter in a cycle that dampens the temperature extremes that would otherwise occur in the absence of this thermal buffering. The seasonal heating and cooling of the ocean's surface drives the vertical circulation of the ocean as well as its horizontal currents. In summer, the warm, light surface water forms a stable layer that resists mixing with the colder, denser water below, a condition called thermal stratification. This stratification isolates the surface layer, preventing the upwelling of cold, nutrient-rich deep water that phytoplankton need to flourish. As a result, the summer surface ocean in many regions is actually relatively poor in nutrients despite receiving abundant sunlight, leading to the somewhat counterintuitive pattern known as the ocean desert, where the warmest surface waters in subtropical regions support less biological productivity than the colder waters of high latitudes. In autumn and winter, cooling of the surface water increases its density until it sinks, breaking down stratification and allowing deep, nutrient-rich water to rise to the surface. This seasonal overturning is what drives the autumn and winter phytoplankton blooms in temperate ocean regions and the spring bloom that follows the return of sunlight to well-mixed, nutrient-rich waters. The thermohaline circulation, sometimes called the ocean conveyor belt, is a global system of deep ocean currents driven by density differences in seawater that arise from temperature and salinity variations. This system has a strong seasonal component in the high-latitude regions, where the deep water that drives the circulation is formed. In the North Atlantic, cold winter winds chill the surface water until it becomes dense enough to sink to the bottom of the ocean, initiating the deep water formation that drives the thermohaline circulation. This deep water then flows southward along the ocean bottom, eventually upwelling in other parts of the world, ocean, and completing the global circulation loop. The intensity of this deep water formation varies seasonally, reaching its peak during the coldest winter months, when surface cooling is most intense. And it varies on longer timescales as well in response to climate changes that affect ocean temperature and salinity. The seasonal cycle of ocean heat storage and release creates the distinction between maritime and continental climates. That is one of the most important features of regional climate geography. Maritime climates, found in regions with ocean on the windward side, experience mild winters and cool summers because the ocean moderates temperature extremes. In winter, the relatively warm ocean releases stored heat to the atmosphere, preventing the extreme cold that would otherwise develop, while in summer, the relatively cool ocean moderates the warming that would otherwise occur. Continental climates, found in regions far from ocean influence, experience the full range of seasonal temperature extremes without this maritime moderation. The city of Vladivostok in Russia and the city of Seattle, Washington in the United States are at almost exactly the same latitude, but Seattle has an average January temperature about 12 degrees Celsius warmer than Vladivostok because of its exposure to the warm North Pacific, while Vladivostok is dominated by cold continental air masses from the Siberian interior. The seasonal migration of ocean currents and the associated patterns of upwelling and nutrient availability drive some of the most important ecological phenomena in the marine world. The California Current, flowing southward along the western coast of North America, brings cold, nutrient-rich water to the surface through seasonal upwelling, particularly in spring and summer, when alongshore winds drive surface water offshore and cold, deep water rises to replace it. This seasonal upwelling sustains some of the most productive ocean fisheries in the world, supporting enormous populations of anchovies, sardines, salmon, and the marine mammals and seabirds that feed on them. The seasonal timing of this upwelling and the interannual variability imposed on it by climate patterns like El Niño determines the productivity of these fisheries from year to year and has profound consequences for coastal fishing communities that have depended on them for centuries. The ocean's seasonal heat engine is thus one of the most important mediating factors between the raw astronomical forcing of the seasons and the climate that organisms and human communities actually experience. Without the ocean's enormous thermal inertia, its capacity to store summer heat and release it in winter, the seasonal temperature swings of the temperate latitudes would be far more extreme, and the winter habitability of maritime regions like Western Europe would be dramatically reduced. The ocean takes the sharp, precisely timed astronomical pulse of the seasons and smooths it into the more gradual, more moderate seasonal rhythm that characterizes the climates where most of humanity lives. High in the upper troposphere, roughly 10 to 15 kilometers above the surface of the Earth, rivers of extremely fast-moving air circle the globe in sinuous, shifting paths that bear only the slightest resemblance to the neat horizontal bands they might appear to be on a simplified diagram of atmospheric circulation. These are the jet streams, and they are among the most powerful and consequential features of the global atmosphere, moving at speeds of 150 to 400 kilometers per hour in their strongest sections. They steer the low-pressure systems that bring rain, wind, and storms to the mid-latitudes. They separate regions of warm and cold air in a continuous dynamical contest, and they shift their position dramatically with the seasons in response to the same axial tilt and differential solar heating that drives all of the season's other manifestations. Where the jet streams are in any given week largely determines the character of the weather for hundreds of millions of people, and the fact that their position changes systematically with the seasons is one of the most important and least appreciated aspects of the seasonal cycle. The polar jet stream. The more powerful and meteorologically significant of the two main jet streams in each hemisphere is driven by the temperature contrast between polar and subtropical air masses. The greater the temperature difference between the cold polar region and the warmer subtropical region at a given altitude, the stronger the pressure gradient in the upper atmosphere, and the faster the wind that flows along that gradient. The physical mechanism is rooted in the relationship between atmospheric temperature and pressure. Cold air is denser and exerts lower pressure at upper levels than warm air, and this horizontal pressure gradient drives the jet stream along the boundary between the two air masses. In summer, the polar regions are warmer than in winter because the extended daylight of the polar summer, combined with the long days at lower latitudes, reduces the temperature contrast between the tropics and the poles. The polar jet stream responds by awakening and migrating poleward. In summer, the jet stream is typically positioned at higher latitudes, allowing warm subtropical air masses to extend further poleward and giving the mid-latitudes their characteristic summer warmth. The weather patterns associated with the summer jet are generally more stable and slower moving than those of winter, with long-lasting high-pressure systems delivering weeks of settled weather alternating with occasional summer storms. In winter, the dramatic cooling of the polar regions, driven by months of reduced solar input or polar night, creates an intense temperature contrast with the relatively warmer subtropical and tropical regions. The jet stream strengthens dramatically and migrates equatorward, its intensified winds channeling powerful winter storms across the mid-latitudes. The winter jet stream over North America can carry winds of 300 to 400 kilometers per hour at aircraft cruising altitude, and it steers the parade of low-pressure systems that bring the rain, snow, and severe weather of the winter season to the eastern United States and Europe. Flights from North America to Europe take advantage of the tailwinds of the winter jet stream, completing the crossing in significantly less time than the return trip against the headwind. The waviness of the jet stream, a property that meteorologists call the Rossby wave amplitude, has important consequences for the character of weather patterns at the surface. When the jet stream is relatively straight and fast-flowing, it tends to move weather systems quickly from west to east, preventing any single weather pattern from persisting very long in any given location. When the jet stream becomes more wavy, developing large north-south meanders called Rossby waves, or long waves, it creates conditions for blocking patterns in which high-pressure systems become nearly stationary for a week at a time. These blocking events are responsible for the most extreme weather, extended heat waves in summer when a blocking high parks warm air over a region for weeks, and prolonged cold spells or flooding episodes in other locations where the jet stream's southward loop carries cold polar air, or persistent precipitation systems. Research over the past 2 decades has suggested a possible connection between the warming of the Arctic, which is proceeding faster than global warming in lower latitudes, and changes in the behavior of the polar jet stream. The hypothesis, associated particularly with the work of scientists Jennifer Francis and Stephen Vavros, proposes that as the Arctic warms faster than the mid-latitudes, the temperature contrast driving the jet stream decreases. The jet weakens, and its meanders become larger and slower moving. If correct, this mechanism would link Arctic warming to more frequent and persistent extreme weather events in the mid-latitudes, including heat waves, cold snaps, droughts, and flooding. The hypothesis remains contested among meteorologists, with some studies supporting it and others finding the evidence insufficient. But it has become one of the most actively debated questions in climate science. The seasonal migration of the jet stream is also closely connected to the monsoon systems that govern rainfall across large parts of the tropics and subtropics. The South Asian monsoon, which delivers the rainfall that sustains agriculture and water supplies for over 1 billion people in India and neighboring countries, is associated with the seasonal migration of the jet stream northward over the Asian continent in late spring and early summer. The jet stream's departure from its winter position over the Himalayas is one of the key atmospheric events that allows moist tropical air to flow northward from the Indian Ocean over South See initiating the monsoon rains. The timing and strength of this jet stream migration varies from year to year, and these variations are among the most important drivers of year-to-year variability in monsoon rainfall. For the ordinary experience of the weather, the seasonal shift of the jet stream is the single most important determinant of what the seasons feel like in the mid-latitudes. The reliable westerly winds and storms of autumn and winter, the relatively settled and warm conditions of summer, the transitional periods of April showers and October gales, all of these familiar seasonal weather patterns are expressions of the jet stream's position and behavior, which in turn is driven by the seasonal change in the temperature contrast between the poles and the tropics, which is itself driven by the 23.5-degree tilt of Earth's axis and its consequences for the distribution of solar energy across the planet. In January 2019, a weather event captured global media attention in a way that few purely meteorological phenomena managed to do. Temperatures across the American Midwest plunged to levels that had not been seen for decades. In Chicago, the temperature fell below -30 degrees Celsius, colder than the surface of Mars on that particular day. Wind chills drove effective temperatures to -48 in some locations. More than 20 people died from cold exposure. Dozens of cars and trucks were abandoned on highways. Schools, businesses, and transit systems shut down across multiple states. The cause of this extreme cold event was reported, with varying degrees of accuracy, as the polar vortex, a term that entered popular vocabulary almost overnight and became the shorthand explanation for extreme winter cold events in the years that followed. But what is the polar vortex, and why does its behavior have such dramatic consequences for the mid-latitude winter? The polar vortex is not a new phenomenon invented to explain modern extreme weather. It is a permanent feature of the winter atmosphere that has existed as long as Earth has had the axial tilt and seasonal cycle that it does today. More precisely, there are two polar vortices, one at each pole, and they are large-scale, persistent circulations of cold air that form in the stratosphere, the atmospheric layer above the weather-producing troposphere, at high latitudes during winter. The northern polar vortex forms in autumn as the Arctic begins losing sunlight and the stratospheric air over the pole cools dramatically, and it strengthens through the winter until the return of spring sunlight begins to warm the polar stratosphere, and the vortex weakens and breaks down. The polar vortex forms for the same reason that jet streams form: temperature contrast. As the polar stratosphere cools to extreme temperatures as low as -80 or even -90 degrees Celsius at its coldest, while the subtropical stratosphere remains relatively warm, the resulting temperature gradient drives strong westerly winds that encircle the pole. These winds form the boundary of the polar vortex, effectively trapping the coldest Arctic air within the vortex and preventing it from spreading southward into the mid-latitudes. When the polar vortex is strong and well-organized, its winds maintain a tight circular boundary that keeps the most extreme cold confined near the pole. The mid-latitude winter, while cold by summer standards, is moderated by the vortex's containment of the deepest cold. The problems for mid-latitude residents begin when the polar vortex weakens and becomes disrupted. This can happen in several ways. Sudden stratospheric warming events, which occur when a pulse of atmospheric waves generated in the troposphere propagates upward into the stratosphere and deposits its energy there, and dramatically and rapidly warm the polar stratosphere, disrupting the temperature gradient that maintains the vortex and causing it to weaken, split, or be displaced from its usual position over the pole. When the polar vortex is disrupted in this way, its confining boundary weakens, and the cold Arctic air it was containing can spill southward in large tongues that push deep into the mid-latitudes. These cold air outbreaks, colloquially called polar vortex disruptions, are the source of some of the most extreme winter cold events in North America, Europe, and Asia. The 2019 event in the American Midwest was a classic polar vortex disruption, a sudden stratospheric warming event in early January 2019 severely disrupted the polar vortex, causing it to split into two separate cells and allowing a lobe of extremely cold Arctic air to descend southward over North America. The temperature records broken during that event in Chicago, Iowa, and across the upper Midwest were genuinely extreme by historical standards, reflecting the unusual depth and persistence of the cold air mass that had been displaced from its polar prison. Within days, the cold air mass moved on, and temperatures returned toward normal, illustrating both the violence of these events and their typically short duration. The relationship between the polar vortex and climate change is one of the most actively debated questions in contemporary climate science. The question is whether the warming of the Arctic, which is proceeding roughly twice as fast as the global average warming, is making polar vortex disruptions more frequent or more severe. The logic of the hypothesis is parallel to that of the jet stream connection. As the Arctic warms, the temperature contrast between the polar stratosphere and lower latitudes decreases, potentially weakening the polar vortex and making it more susceptible to disruption by the atmospheric waves that originate in the troposphere below. If the vortex is more easily disrupted, more frequent and severe winter cold outbreaks could occur in the mid-latitudes even as the overall climate warms. This hypothesis produces one of the apparent paradoxes of climate change. Warming could make extreme winter cold outbreaks more frequent in some regions, at least in the near term. The evidence for this connection is mixed and the debate in the scientific literature continues. But several recent studies have found statistical associations between low autumn Arctic sea ice extent, which is itself a consequence of warming, and subsequent winter cold events in the mid-latitudes. The physical mechanisms connecting these observations are still being worked out. The polar vortex is ultimately one of the most dramatic expressions of the seasonal imbalance of solar heating that the axial tilt creates. The winter pole, deprived of sunlight for months, becomes the coldest place in the lower atmosphere, and the intense cold it accumulates is the raw material of every polar vortex event. The vortex is winter's cold core, the concentrated reservoir of the darkest and most extreme consequences of the season, contained for most of the winter by its own circulating winds and released in powerful and frigid pulses when those winds falter. 600 million people in South Asia wait for it every year. In late May and early June, the sky over the southern tip of India and the Bay of Bengal begins to change. The heat that has been building since April, the brutal, dry heat of the pre-monsoon season, when temperatures reach 45 degrees Celsius across the Ganges plain and reservoirs shrink to puddles, gives way to a new quality in the air, a heaviness, a smell of rain from the south, a darkening of the sky at the horizon that grows day by day. Then the rains arrive, first at the coast, then spreading northward across the subcontinent. Over the course of weeks, the monsoon transforms the landscape with an abruptness that seems almost theatrical. The rivers run again, the fields green up, the dust settles, the temperature drops. For a civilization that has been built over 3,000 years around the reliable arrival of these rains, the monsoon is not merely a weather event, but the organizing principle of the year, the heartbeat of the agricultural calendar, the subject of more poetry, prayer, and practical calculation than perhaps any other natural phenomenon in human history. The word monsoon comes from the Arabic mawsin, meaning season, and it refers specifically to a seasonal reversal of wind direction, associated with a dramatic change in precipitation. The classic monsoon system of South Asia involves dry, cold winds blowing from the northeast across the subcontinent in winter, when the Asian landmass is cold and high pressure dominates the region, and warm, moisture-laden winds blowing from the southwest in summer, when the heated continent draws in moist air from the Indian Ocean. This seasonal reversal of wind direction, from northeast to southwest and back again, is the defining feature of the monsoon circulation, and the reason it delivers such dramatically different amounts of precipitation and wind terror in summer. The physical mechanism of the monsoon is essentially a giant sea breeze operating at the scale of an entire continent. A simple sea breeze, familiar to anyone who has spent time at the coast occurs because land heats up faster than water during the day, creating a low-pressure area over the hot land and drawing cooler, denser air from the sea inland. At night, the land cools faster than the sea. The pressure gradient reverses, and a land breeze blows from the cooled land back out over the warmer water. The monsoon is this same phenomenon operating at a continental scale and on a seasonal rather than daily time scale. During Northern Hemisphere summer, the Asian continent heats up enormously under the relentless sun, creating a vast area of low pressure over the interior. The surrounding oceans, which have been accumulating heat but are far more resistant to temperature change than the land due to their high heat capacity, remain cooler. The pressure difference draws moist maritime air from the Indian Ocean northward and northeastward over the continent, and as this moist air rises over the heated land and the mountain barriers of the Western Ghats and the Himalayas, it cools adiabatically and releases its moisture as rain. The Himalayas play a crucial role in the South Asian monsoon that goes beyond simply providing a barrier that forces air to rise and precipitate. The Great Mountain Chain acts as a thermal barrier that prevents cold, dry air masses from the north from penetrating into the Indian subcontinent during the summer monsoon season, maintaining the warm conditions that sustain the low-pressure system. Driving the monsoon, the Tibetan Plateau, elevated to an average of over 4,000 meters above sea level, absorbs an enormous amount of solar energy during summer and heats the upper atmosphere above it to temperatures significantly warmer than the surrounding atmosphere at the same altitude, creating an elevated heat source that acts as a pump drawing air into the monsoon circulation from the south. The monsoon is not a single entity, but a complex system of interacting circulations that has different manifestations across South Asia, East Asia, Southeast Asia, West Africa, Australia, and the Americas. The West African monsoon delivers the rains on which agriculture across the Sahel depends, its northward penetration each year determining whether rainfall will be adequate for crops or whether drought will prevail. The East Asian monsoon system delivers the rain that fills the reservoirs and irrigates the rice paddies of China, Japan, and Korea. The Australian monsoon brings summer rains to the northern part of that continent. All of these regional monsoon systems share the same fundamental mechanism: seasonal reversal of wind direction driven by the temperature contrast between a heating continent and the surrounding ocean. The seasonal timing and intensity of monsoons are among the most critical and most variable aspects of the seasonal cycle for the people who live within their influence. Year-to-year variations in the strength and timing of the South Asian monsoon have profound consequences for agriculture, water supply, and the incidence of flooding. A weak or late monsoon can lead to drought and crop failures across hundreds of millions of hectares. A particularly intense monsoon can cause catastrophic flooding in river basins where the infrastructure for managing extreme flows is inadequate. The ability to forecast the monsoon months in advance has been a major goal of meteorological science for over a century. And while significant progress has been made, the monsoon remains one of the most challenging systems to predict accurately at seasonal timescales. The monsoon is also deeply implicated in the climate change story. Model projections consistently indicate that the South Asian monsoon will intensify in a warming climate, delivering more precipitation in the wet season, while the dry season may become drier in some regions, a pattern of increased variability that is sometimes described as wet seasons getting wetter and dry seasons getting drier. The intensification of the monsoon is driven by the greater evaporation from warmer oceans, which loads the monsoon air masses with more water vapor, and thus increases the potential for heavy precipitation. At the same time, changes in the land surface associated with deforestation, agricultural expansion, and urbanization are modifying the regional temperature contrasts that drive monsoon circulations, adding another layer of complex system. Every autumn across the temperate forests of North America, Europe, and East Asia, a transformation occurs that draws millions of tourists to witness it, and that has inspired more poetry, painting, and philosophical reflection than almost any other natural event. The leaves of deciduous trees, which have maintained their green through the long summer, begin to change. First, a few trees on exposed hilltops show hints of orange and red. Then the colors spread downhill and across the landscape, gaining intensity day by day until the forest blaze with a spectacle of yellow, orange, red, purple, and brown that seems designed for human appreciation. Then, as suddenly as it began, the display ends. The leaves fall, the branches are bare, and winter arrives. This annual drama is one of the most beautiful expressions of the seasonal cycle in the natural world, and it is governed by a precise and elegant biochemical system that reads the shortening of autumn days and initiates a complex cascade of physiological changes in preparation for the cold months ahead. The first thing to understand about autumn leaf color is what it is not. It is not caused by the cold. This is one of the most persistent misconceptions about the phenomenon. While cold temperatures can intensify certain colors, particularly the reds and purples, and while cold nights are associated in most people's experience with peak autumn color, the trigger that initiates the entire process is the shortening of the day length rather than the drop in temperature. Trees that are kept at warm temperatures in a greenhouse but given artificially short days will begin the physiological preparation for leaf drop and show autumn coloration on the same schedule as trees experiencing natural autumn conditions. Trees given long days but cold temperatures will delay their color change. Day length is the primary trigger. Temperature is a modifying factor. The reason trees change their leaves in autumn, rather than simply keeping them through the winter as conifers do with their needle-like leaves, is fundamentally an economic calculation written in the language of biochemistry and evolution. The broad, flat leaves of deciduous trees are highly efficient photosynthetic organs, capturing a large area of sunlight for energy production during the long, warm, brightly lit days of summer. But they are also costly to maintain. They require significant amounts of nitrogen and other nutrients to keep the photosynthetic machinery running, and they are vulnerable to physical damage from frost and ice loading. In winter, when the days are short, temperatures are cold, and photosynthetic productivity would be minimal, the cost of maintaining these large leaf surfaces outweighs the benefit. It is more economical for the tree to dismantle the photosynthetic apparatus in the leaves, recover as many of the valuable nutrient compounds as possible, and shed the leaves to wait out the winter as a bare, dormant skeleton. The process of autumn leaf preparation and leaf drop is called senescence and abscission, and it begins weeks before the leaves actually fall. As day length shortens past a species-specific threshold, the leaf receives a signal to begin dismantling its photosynthetic apparatus. The most abundant pigment in summer leaves, chlorophyll, which gives them their green color and is responsible for capturing light energy for photosynthesis, begins to break down. Chlorophyll is a molecule that degrades relatively rapidly in the light and must be continuously synthesized throughout the growing season to replace the degraded molecules. When the senescence signal arrives, chlorophyll synthesis stops, and the existing chlorophyll degrades without replacement. As the green chlorophyll fades, it reveals the other pigments that were present in the leaf, all along but masked by the dominant green. Carotenoids, the yellow and orange pigments that give autumn leaves their golden and amber tones, are actually present in leaves throughout the growing season, playing accessory roles in photosynthesis by capturing wavelengths of light that chlorophyll cannot use efficiently. They are more chemically stable than chlorophyll and persist longer into the senescence process, becoming visible as the chlorophyll disappears. This is why yellow and orange are the most reliably produced autumn colors, visible every year in species like aspens, birches, hickories, and ginkgos regardless of weather conditions. The red and purple pigments of autumn, the colors that make New England maple forests, or the mountainsides of the Japanese autumn particularly spectacular, are a different story. These colors are produced by anthocyanins, pigments that are newly synthesized in the leaf during autumn senescence, rather than being revealed from underneath the disappearing chlorophyll. Anthocyanin synthesis requires warm sunny days, combined with cool nights, conditions that favor the accumulation of sugars in the leaf that serve as precursors for anthocyanin production. This is why the intensity of red color in autumn leaves is highly dependent on the weather. An autumn with warm, sunny days and cold, clear nights produces the most vivid reds, while a cloudy, warm autumn tends to produce more muted yellows and browns. The function of anthocyanin production in senescing leaves is not fully understood and is an active area of research in plant biology. The most widely accepted current hypothesis is that the red pigments provide a kind of sunscreen for the leaf during the critical period of nutrient recovery, protecting the leaf's cellular machinery from photooxidative damage while the chlorophyll is being dismantled and the valuable nitrogen it contains is being chemically recovered and transported into the woody tissue of the branch for storage over winter. A leaf that retains chlorophyll during senescence but cannot complete the nutrient recovery process efficiently is like a factory that is still exposed to damaging conditions while trying to dismantle itself. The anthocyanin screen may protect against this damage and allow more complete recovery of the investment represented by the leaf's nitrogen content. The autumn color display is therefore not merely beautiful. It is one of the most precisely orchestrated biochemical responses to the seasonal cycle in nature, a cascade of molecular events triggered by the shortening of the day and culminating in the efficient dismantling and recycling of a complex biological structure that served the tree for one growing season. The colors are the visible trace of this molecular dismantling, the spectrum of chemistry that emerges when the dominant green of active photosynthesis is removed, and the underlying biochemistry of preparation, protection, and recovery is revealed. In late June above the Arctic Circle, the tundra is almost unrecognizable to anyone who knows it, only from photographs taken at other times of year, where the landscape is brown, snow-covered, and apparently dead for 8 or 9 months of the year. It is now carpeted in a dense, colorful growth of sedges, grasses, wildflowers, mosses, and lichens, packed together as tightly as any garden, their small forms making the most of every centimeter of ground. The air is thick with insects. Shorebirds crowd every wetland. Lemmings tunnel through the vegetation. In the shallow ponds, insect larvae and crustaceans are developing at frantic speed. The sun circles overhead without setting, providing a continuous if low-angled supply of energy to this explosion of life. And ticking beneath all of it is a clock that everyone and everything in this ecosystem can feel. The biological awareness that this abundance is temporary. The winter is coming back, the darkness will return, and every species that wants to complete its annual cycle of growth, reproduction, and preparation for survival must do so within the brief window that the Arctic summer provides. The brevity of the Arctic growing season is extreme even by the standards of other challenging environments. At 70 degrees north latitude, the frost-free season, the period between the last spring frost and the first autumn frost, may be only 6 to 8 weeks long. In some years and at higher latitudes, it can be shorter still. Compare this to the 6-month frost-free season of the mid-temperate zone, or the year-round growing conditions of the tropics, and the challenge facing Arctic organisms becomes clear. Everything that needs to happen in the annual biological cycle, germination, growth, flowering, pollination, seed set, larval development, fledging, fattening, and the preparation for winter dormancy or migration, must be compressed into this 6 to 8 week window. Arctic plants have evolved a range of strategies for surviving and reproducing under these extreme time constraints. Most Arctic plant species are perennials rather than annuals, because the growing season is too short to complete the entire life cycle from seed to seed in a single year. Perennial plants can spend multiple years building up their root systems and stored energy reserves before investing in a flowering effort, spreading the cost of reproduction across several years of slow growth rather than attempting to accomplish it all in one season. Many Arctic plants can begin photosynthesis almost immediately as snow melts, having formed their leaf structures under that snowpack in early spring and simply waiting for the covering to melt rather than having to grow new leaves from scratch. The dwarf growth form of most Arctic plants is itself a temperature adaptation that is also a time-saving strategy. Temperatures just above the ground surface in the Arctic can be significantly warmer than temperatures at standing height because the dark soil and vegetation absorb solar radiation and create a warm microclimate in the few centimeters immediately above the ground. Low-growing plants exploit this thermal advantage. A plant that keeps all its leaves within a centimeter of the warm soil surface is effectively growing in a microclimate several degrees warmer than a plant that extends its leaves half a meter into the air. This thermal advantage can mean the difference between completing growth and reproduction within the frost-free window, or failing to do so. Arctic insects, particularly mosquitoes, midges, and other flies, are present in almost inconceivable numbers during the brief summer, a density of biomass that staggers visitors but makes biological sense in the context of the compressed season. Immense numbers are needed because the adults have only weeks to find mates and lay eggs before the cold returns. The biting insects that make the Arctic summer so uncomfortable for warm-blooded visitors are an essential component of the ecosystem. They are the primary food of many of the migratory shorebirds and songbirds that travel thousands of kilometers to breed in the Arctic. Without this seasonal flush of insect biomass, the Arctic would not be able to support the enormous numbers of breeding birds that depend on it. The timing of reproduction in Arctic breeding birds has been fine-tuned by natural selection to match the peak availability of insects with the period of maximum chick food demand. Most Arctic breeding shorebirds, for inns, tants, time their egg laying so that their chicks hatch at the moment when insect abundance is expected to be at its peak. The lag between egg laying and hatching is used as a predictive buffer. By laying eggs a few weeks before peak insect abundance, the birds ensure that the most energy-demanding phase of chick rearing, when the chicks are growing fastest and eating most, coincides with the most productive period of the Arctic summer. Climate change is disrupting this timing by causing the peak of insect emergence to occur earlier in the season, while the birds' migratory timing, which is controlled by day length at their wintering grounds, has advanced more slowly, creating a growing mismatch between the food peak and the peak food demand. The return of the darkness is not a distant threat that Arctic organisms can ignore until autumn arrives. The physiological preparation for winter begins before the summer is over, while the sun is still circling the sky without setting. Arctic ground squirrels, which hibernate through the 10 months of Arctic winter and emerge for only about 2 months of summer, begin accumulating fat stores almost immediately upon waking from hibernation, spending the entire brief summer in a state of hyperphagia that maximizes their caloric intake. Migratory shorebirds begin their southward migration from the Arctic in July, before the summer is technically over, some of them departing before their chicks are even fully independent, in a race to reach staging areas where they can fatten before their long southward journey. The urgency is real and biological. In the Arctic, the preparation for the returning dark is not an autumn activity, but a summer one. When we speak of the 4 seasons in English, we are using a cultural framework so deeply embedded in the language and traditions of temperate Europe and North America that it can feel like a universal description of reality rather than a particular cultural choice. The 4-season model, with spring, summer, autumn, and winter each distinct and recognizable, is genuinely well-suited to the climates of Western and Central Europe, where the temperate maritime and continental climates produce 4 relatively distinct phases of the year, but impose this framework on the climate and culture of South Asia, Sub-Saharan Africa, Southeast Asia, or Australia, and the inadequacy of the 4-season model immediately becomes apparent. The world has many more ways of dividing the year than 4, and the diversity of seasonal frameworks across human cultures reflects the genuine diversity of the climates that those cultures have adapted to and understood over thousands of years. In much of South Asia, traditional cultural and agricultural calendars recognize 6 seasons rather than 4, a system that has deep roots in Sanskrit literature and ancient Indian astronomical and meteorological observation. The 6 seasons of the Hindu calendar, called the Shadritu, divide the year into pairs of months: Vasanta or spring in March and April, Grishma, or summer in May and June. Varsha, or the monsoon season in July and August. Sharada, or autumn in September and October. Hemanta, or pre-winter in November and December. And Shishira, or winter in January and February. This six-season division reflects the genuine meteorological reality of the Indian subcontinent, far better than the four-season model, capturing not just the temperature and day-length changes that the four-season model tracks, but also the critical distinction between the monsoon season and the dry seasons on either side of it. The monsoon season, Varsha, is so ecologically and economically significant in India that its recognition as a distinct season separate from summer is not a cultural luxury, but a practical necessary. The arrival of the monsoon transforms the landscape, the agriculture, the hydrology, and the social life of the subcontinent more dramatically than any other seasonal transition. Failing to distinguish it from the summer that precedes it, or the autumn that follows it, would be like failing to distinguish winter from autumn in a climate where snow and ice make the January landscape unrecognizable from the October one. The six-season system reflects the fact that South Asian meteorology genuinely has six distinct phases, and that the communities that developed this framework were careful and accurate observers of the seasonal cycle they lived within. Many Aboriginal Australian peoples traditionally recognized two main seasons rather than four, organized around the wet and dry periods that dominate the northern Australian climate. The Yolngu people of Arnhem Land in the Northern Territory recognized the Chuladur, or the dry season, and Barra, the monsoon season, along with the transitional winds and atmospheric changes that precede and follow each. Some Aboriginal communities in Northern Australia recognize up to 6 or 7 seasons, defined not just by rainfall but by the flowering of specific plants, the availability of specific food sources, the behavior of specific animals, and the prevailing wind directions. These detailed seasonal calendars, developed over tens of thousands of years of intimate engagement with the Australian environment, encode ecological knowledge of extraordinary depth and practical usefulness. They are not approximations of Western-style meteorological seasons, but independent and in many respects more detailed classification systems tailored to the specific ecological realities of their regions. In Japan, the traditional calendar system recognized 24 smaller seasonal divisions called seki, dividing the year into periods of approximately 15 years each, corresponding to specific points in the solar cycle. These 24 divisions were further subdivided into 72, even shorter periods called ko, each associated with specific natural phenomena: the first blooming of cherry blossoms, the singing of particular birds, the emergence of particular insects, the ripening of specific foods. This extraordinarily detailed seasonal taxonomy reflects the Japanese cultural tradition of mono no aware, an awareness of and sensitivity to the transience of natural phenomena, that finds expression in the ritual observation of seasonal markers like the cherry blossom, the new green of spring maples, the crimson of autumn maples, and the first snow of winter. The number of seasons recognized by a culture reflects both the climate of its homeland and the aspects of that climate most important to its livelihoods and ways of life. Farming cultures that depend on rain will distinguish wet from dry as carefully as those in temperate climates distinguish warm from cold. Pastoral cultures that move their animals seasonally will recognize the seasons of grass growth and dry season scarcity that govern their herd's welfare. Maritime cultures will recognize the seasons of calm and storm, of favorable and adverse winds that determine when the sea can be safely navigated. The four-season model of the Western tradition is not wrong. It is simply one culturally specific answer to the question of how to divide the continuous flow of time into meaningful, recognizable units based on the seasonal changes most important to the people asking the question. The encounter between different seasonal frameworks in the context of globalization and climate science has produced both productive dialogue and occasional misunderstanding. Climate scientists studying the impact of seasonal change on agriculture, biodiversity, and water resources in different parts of The world have increasingly come to recognize that the four-season model is an inadequate framework for capturing the seasonal complexity of many of the world's climate systems, and there is growing interest in working with local and indigenous seasonal knowledge systems that may provide more accurate and more ecologically meaningful descriptions of seasonal change in specific regions. The idea that a six-season system developed in ancient India or a multi-season system developed by Aboriginal Australians might have scientific value as well as cultural significance is a recognition that the careful long-term observation of seasonal patterns that any human community must undertake to survive in a particular environment produces genuine knowledge, even when it is expressed in cultural rather than scientific language. Imagine resetting Earth from the beginning, the same size, the same distance from the same sun, the same atmosphere, the same oceans. But one thing different: the axial tilt is zero. Earth spins on an axis perfectly perpendicular to the plane of its orbit, upright and unchanging, neither leaning toward the sun at any point in the year nor leaning away. The sun at every latitude rises and sets at the same points on the horizon every single day of every year. Day length everywhere on Earth is always exactly 12 hours. The noon sun always reaches the same altitude in the sky, day after day, week after week, year after year. There are no seasons. There is no summer. There is no winter. There is only an eternal, unchanging climate band at every latitude. As fixed and permanent as the latitude lines themselves, what would this world look like? How would it feel to live in it? And what would the absence of seasons mean for the biology, geography, and culture of such a planet? The most immediate consequence of zero axial tilt would be the elimination of the day-length variation that drives so much of the seasonal biology of the current Earth. Without the long days of summer to deliver extended solar heating, and the short days of winter to allow extended cooling, the temperature at any given latitude would stabilize at a value determined almost entirely by its distance from the equator and its proximity to the ocean, with only the gentle seasonal variation caused by Earth's slightly eccentric orbit producing any year-to-year temperature cycle at all. The equatorial regions would still be hot, the poles cold, and a smooth temperature gradient would connect the two extremes, but within any climate zone the temperature would be almost perfectly constant throughout the year. The climate zones of a zero-tilt Earth would be more sharply defined and more stable than those of our current world. The equatorial belt, receiving nearly overhead sunlight year-round, would be persistently hot and wet, the site of enormous thunderstorm activity driven by continuous intense heating of the surface. Subtropical regions, where the descending branch of the Hadley circulation creates dry conditions, would be persistent deserts without the seasonal monsoon rains that currently make the tropical margins more habitable. The temperate zones would receive consistent, moderate sunlight throughout the year, neither the intense summer sun nor the weak winter sun of current temperate climates. The polar regions would be in perpetual twilight, receiving the sun's energy at extremely shallow angles year-round, rather than getting intense summer sun alternating with winter polar night. The oceans of a zero-tilt Earth would be dramatically different from those of the current world. The seasonal cycle of ocean heating and cooling, which drives the deep mixing and the upwelling of nutrient-rich waters that sustains marine productivity in current temperate and polar oceans, would be absent. Ocean surface temperatures would be determined primarily by latitude, with a permanent warm pool at the equator and cold water at the poles, and the vertical mixing that currently occurs when autumn cooling makes surface water dense enough to sink would not occur. The resulting ocean would likely be more strongly stratified, with less exchange between the productive surface and the nutrient-rich depths, potentially supporting less biological productivity overall. The biological world of a zero-tilt Earth would be transformed beyond recognition. The seasonal cues that govern the timing of virtually every significant biological event in the current biosphere, flowering, breeding, migration, hibernation, leaf fall, would either be absent or based entirely on the much weaker signals of the 3% variation in Earth-Sun distance caused by orbital eccentricity. This tiny residual seasonality, producing at most a 7% variation in total solar irradiance across the year, would likely be too weak to maintain the dramatic seasonal behaviors and adaptations that characterize current life at temperate and polar latitudes. Migration, as a strategy for exploiting different seasonal resources, would make far less sense in a world where the resource availability did not change dramatically across the year. Hibernation in response to winter cold and food scarcity would have no trigger. Plant life on a zero-tilt Earth would be very different from the plants we know. The deciduous trees of current temperate and boreal forests, which shed their leaves each autumn in preparation for a winter cold season, would have no cold season to prepare for, and no short days to trigger their senescence. The boreal forest itself, the great belt of cold-adapted conifers that currently spans the high latitudes of North America and Eurasia and contains roughly 30% of the world's forest carbon, might not exist as a distinct biome. Without winter cold to limit growing season competition from tropical and temperate species, the sharp ecological boundaries between biomes might be replaced by more gradual transitions. Many of the flowering time cues that plants use to avoid competition and to time their reproduction to coincide with the emergence of their pollinators would be absent or altered. For human civilization, the absence of seasons would mean the absence of much of what makes human cultural diversity so rich and so distinctive. The agricultural calendars, the seasonal festivals, the cycle of planting and harvest that have structured human time for 10,000 years would all be based on very different rhythms or might not exist at all. A civilization developing on a zero-tilt Earth would have no concept of winter as a cold and dark season, no experience of the drama of spring's return, no autumn harvest festival marking the end of the growing season, no celebration of the solstice as a cosmic turning point. Their year would be the same, round and smooth, in January as in July, in the northern hemisphere as in the southern. The contrast between such a world and the world we actually inhabit is the measure of what the 23.5-degree tilt actually gives us. It gives us the drama of the seasons, the biological diversity that seasonal environments support, the cultural richness that seasonal rhythms generate, and the deep body-felt knowledge that time is not circular but spiraling, that each year is the same in its broad structure but different in its details, that the world changes and returns and changes again in a rhythm that is at once completely predictable and endlessly surprising. The tilt is the generator of seasons, and the seasons are the generator of much of what makes life on Earth, and human life in particular, so extraordinary, varied, so deeply beautiful, and so persistently meaningful.